Hello there and welcome to Science for Sleep, where curiosity is never in a rush and science enjoys taking the long way round. Tonight's gentle exploration begins far, far back in time. Not hundreds of years ago, or thousands, or even millions. We're going to drift together to the very beginning of everything you've ever known, to a moment when the universe was so new it was still figuring itself out. Imagine a cosmos that has only just begun to exist. The space around you isn't just empty, it's freshly minted, expanding faster than your mind can follow. Energy and matter are tangled together in a frenzy of creation. This is the scene, if scene is the right word, just after the Big Bang. And in that moment, the question that will quietly guide our whole journey tonight is simple, but full of wonder. Could life, in any form, have started almost immediately? Was the universe ready to welcome living things right after it came into being? Or did it need an unimaginably long time to prepare the stage? We're going to take our time with this one, because the story isn't short, and the answer depends on details that unfolded over billions of years. There's no hurry here. Just settle into wherever you are right now, feel the day slow down, and let's begin following the thread together. I'm curious. Where are you listening from this evening? Are you in a busy city with streetlights outside your window, or somewhere quieter where the stars are already visible? If you look up right now, you're seeing light that has crossed space for years, decades, or more. Some of those tiny pinpricks have been shining since the universe was young. And here you are, in your own little spot in space and time, about to think about the very first moments of existence. If you find this kind of slow, calm wondering to be a welcome break from the rush of the day, it would mean a lot if you gave this a like and maybe subscribed. It helps others find their way to this little corner where science and rest meet. You might even share it with someone who could use a soft journey into the history of everything. The Big Bang, despite the name, wasn't an explosion in space. It was the rapid expansion of space itself from an unimaginably small, hot and dense state. Before it, as far as our best understanding goes, there was no space and no time in the sense we usually mean. Everything began in that moment, and from there, the universe has been expanding and cooling ever since. In the first fraction of a second, the conditions were so extreme that ordinary matter as we know it couldn't exist. Instead, it was a churning sea of fundamental particles, quarks, electrons, neutrinos, mixed with intense radiation. In those early instants, the temperature was trillions of degrees. If you could somehow be there, not that survival would be possible, there would be no solid surfaces, no atoms, and certainly nothing like the complex chemistry that life depends on. The basic building blocks of matter were colliding constantly, forming and breaking apart again in an endless exchange of energy. Gravity, electromagnetism, and the nuclear forces were all in play, shaping the behaviour of this new reality. Even in that chaos, the first seeds of structure were being sown. The expansion of space caused the temperature to drop rapidly, and as it did, quarks began to combine into protons and neutrons. That took place within the first few minutes, and those protons and neutrons would eventually become the nuclei of atoms. But we're getting ahead of ourselves. At this point, everything was still so hot that electrons couldn't stay bound to nuclei, so there were no neutral atoms yet. The reason this matters for our question about life is simple. Life as we understand it requires complex atoms, carbon, oxygen, nitrogen, and others, combined into molecules, and those atoms didn't exist yet. For now, hydrogen and helium were the main products, with a small trace of lithium. The heavier elements that make up planets, oceans, and living cells would only come much later, through processes inside stars. So in these first minutes, the universe was not ready for life in any familiar form. Still, there's something remarkable in realizing how quickly the basics came together. Within minutes, the building blocks for most of the matter in the universe had formed. The hydrogen atoms that make up the water in your body were born in that early window. Every breath you take contains atoms that have been here since almost the very beginning. After this initial flurry of creation, the universe kept expanding and cooling. Radiation dominated over matter for a long while, and space was filled with an almost uniform glow. This glow, stretched by billions of years of expansion, is what we now see as the cosmic microwave background. It's a faint echo of that time, and it tells us that the young universe was astonishingly smooth. There were only tiny variations in density, but those tiny differences were enough for gravity to slowly begin gathering matter together into clumps. But in these early tens of thousands of years, there was still no light in the way we think of starlight. Space was a hot fog of particles and photons, constantly scattering off each other. Only after about 380,000 years did things cool enough for electrons to settle into orbits around nuclei, forming neutral atoms. At that moment, light could travel freely, and the universe became transparent for the first time. That was an important step, but it still wasn't the sort of environment where life could form. The only elements present were the simplest ones. No planets yet, no complex molecules. Thinking about life right after the Big Bang also means thinking about time in a way we don't often do. When we say right after, we might mean seconds, minutes, or years. But in cosmic terms, even hundreds of millions of years can count as soon. Life on Earth didn't appear until the universe was more than 9 billion years old. That's an enormous gap compared to the entire age of the universe, which is about 13.8 billion years. If life had appeared right after the Big Bang, it would mean conditions came together vastly faster than they did here. So, was it physically possible? Not in the first minutes or thousands of years. The chemistry wasn't ready, the materials weren't there, and the energy levels were too extreme. But as the first stars began to form hundreds of millions of years later, something new became possible. Inside those stars, the heavier elements were forged, and when the stars died, those elements were scattered into space. Only then could planets form with the complex chemistry needed for life. From our perspective now, those hundreds of millions of years feel impossibly long. But for the universe, they were just the early steps of a much longer story. The pace of cosmic evolution is slow compared to the rhythm of human life, but that slowness was essential. If the universe had somehow rushed the process, the conditions for stable, life-supporting environments might never have developed. Right now, as you're listening, light from those earlier stars is still travelling toward us, stretched into faint infrared wavelengths by the expansion of space. We're only just beginning to see them with our most powerful telescopes. They show us a universe that was already busy building the foundations for everything that would follow. And in that light, we can see the moment when the question, was the universe ready for life, started to shift from a simple no to a cautious maybe. We can move gently deeper into the story, following how those first stars changed everything, and how the cosmic landscape evolved from a sea of hydrogen and helium into something far more varied. The changes were slow but steady, and with each passing million years the conditions became just a little more favourable for the possibility of living worlds somewhere in the vastness. The moment after the Big Bang is difficult to picture, not just because it was so far in the past, but because the physical reality was unlike anything we encounter today. It wasn't a space filled with objects, it was space itself expanding, carrying with it the raw ingredients of matter and energy. If you could somehow stand outside and look in, though there was no outside to stand in, you wouldn't see planets or stars or anything familiar. You'd be watching the very rules of the universe taking shape while the contents churned and shifted in extreme conditions. In the first trillionth of a second, the temperature was so high that even the most basic particles couldn't hold together for long. Quarks and gluons moved freely in what physicists call a quark-gluon plasma, a dense and energetic state where the boundaries between matter and radiation were blurred. Forces that today are separate, gravity, electromagnetism, the strong and weak nuclear forces, were in different relationships than they are now. As the universe expanded, these forces separated, a process known as symmetry breaking. It's an unassuming term for a series of events that determined how matter would behave forever after. Within that early plasma, energy was converting into particles, and particles back into energy, according to Einstein's famous equation. The density was extraordinary, the pressure immense, and yet, almost instantly by human standards, things began to change. Expansion acted like a cosmic cooling system, and with each fraction of a second that passed, the temperature dropped just enough for new phases of matter to emerge. After a microsecond or so, the quarks began binding together into protons and neutrons. These are the building blocks of atomic nuclei, and they're much more stable than the fleeting particle combinations of earlier moments. The strong nuclear force, which binds quarks inside protons and neutrons, became the dominant factor at that scale, ensuring these particles could survive the increasingly calm but still unimaginably hot conditions. From here, the timescale shifted from fractions of a second to whole seconds, which in this young universe still felt like an eternity. Around 1 second after the Big Bang, the temperature had fallen to about 10 billion degrees Kelvin. That's still beyond anything you'd experience in a star's core today, but low enough for neutrinos, tiny, almost ghost-like particles, to decouple from matter. They began travelling freely through space, carrying with them a record of conditions in that first second. These neutrinos are still out there now, forming what's called the cosmic neutrino background, though detecting them directly is a monumental challenge. 2 to 3 minutes in, a process called Big Bang nucleosynthesis began in earnest. Protons and neutrons started to combine into the nuclei of the lightest elements. Most became hydrogen nuclei, single protons, but some fused into helium nuclei made of 2 protons and 2 neutrons, and a trace amount of lithium and beryllium. This period lasted for only about 20 minutes before the density and temperature dropped too low for further fusion to occur. From that point onward, the elemental makeup of the universe was set at roughly 75% hydrogen, 25% helium by mass, and tiny traces of lithium and other light nuclei. This was a decisive step toward a universe that could eventually support life, but it was still only the beginning. For life as we know it to arise, far heavier elements would be needed, including carbon, oxygen, nitrogen, phosphorus, and iron. Those wouldn't appear until stars had formed and lived long enough to forge them in their cores. So in these first minutes, the universe had taken its first step toward complexity, but the path ahead was long. After nucleosynthesis ended, the young cosmos entered a quieter but still dynamic phase. Photons, the particles of light, were constantly scattering off free electrons, making the universe opaque. No light could travel far without bumping into something, and as a result, space was filled with a hot, uniform glow. Matter and radiation were locked together in this dense, fog-like state. The only variations were minuscule fluctuations in density, tiny ripples in the distribution of matter and energy. These fluctuations were the seeds from which galaxies would eventually grow, guided by gravity over hundreds of millions of years. During this time, the universe continued to expand and cool. Over the next 380,000 years, temperatures dropped from billions of degrees to just a few thousand. When the temperature reached around 3000 Kelvin, a critical change occurred. Electrons could finally bind to nuclei without being immediately knocked away by energetic photons. This recombination of electrons and nuclei created neutral atoms, primarily hydrogen and helium. The formation of neutral atoms meant photons no longer scattered constantly. Light could travel freely for the first time, marking the moment the universe became transparent. That light, stretched by cosmic expansion over billions of years, is what we now detect as the cosmic microwave background. It carries with it an extraordinarily detailed snapshot of the universe at that early stage, so detailed that it's possible to map the faint variations in temperature that reflect those original density ripples. This transparency was important, but even now, there was still no starlight. Space was dark in the visible sense, filled instead with a faint infrared glow from the residual heat of the Big Bang. The first stars wouldn't appear for hundreds of millions of years, and without them, There were no sources producing the heavier elements needed for planets or life. In a way, the universe at this point was like a room that had been furnished with only the simplest tools. It had the basic matter and the physical laws in place, but no complex structures yet. Gravity was beginning its slow work of pulling together those slightly denser regions into larger and larger clumps. But the process was gradual. The matter was still spread thin, and although hydrogen and helium atoms could form simple molecules like molecular hydrogen, the chemistry was limited. It's worth noting that even in this early stage, certain conditions that would one day be relevant for life were already present in rudimentary form. The laws of physics as we know them had settled into their current arrangement, allowing stable matter to exist. The relative amounts of matter and radiation were balanced in a way that permitted structures to form rather than being torn apart by the sheer energy of photons. And the expansion rate set by the initial conditions of the Big Bang was neither too fast nor too slow. Too fast, and matter would never clump together. Too slow, and the universe could have collapsed back on itself before stars and planets had a chance to appear. From our position now, it's tempting to think of these early moments as simply a prelude, but they were more than that. They determined everything that would follow. The ratios of elements produced in the first minutes influenced the chemistry of the first stars. The slight unevenness in density determined the locations of the first galaxies. Even the faint hiss of the cosmic microwave background has subtle variations that act as a blueprint for the large-scale structure of the universe. For the question of whether life could have started right away, the answer in this era is still a definite no. Without heavier elements, without stable planetary surfaces, without liquid water, the kind of life we recognize as living couldn't exist. But the foundation was in place. The universe had matter, the matter had structure, and the conditions were moving in a direction that, given enough time, could make life possible. As the first million years passed, the cosmic fog remained, slowly thinning as neutral atoms became more common. The temperature continued to drop, and the first signs of large-scale gravitational collapse were beginning in those slightly denser patches. In some regions, dark matter, a form of matter that interacts through gravity but not light, was clumping alongside ordinary matter, helping to pull gas together into the precursors of galaxies. Dark matter's role here is crucial, because without its gravitational pull, the gas might not have condensed quickly enough to form stars in a reasonable time frame. By around 100 million years after the Big Bang, the first truly dense regions were ready to ignite star formation. The earliest stars were unlike most stars we see today. They were massive, short-lived, and composed almost entirely of hydrogen and helium. Their great size meant they burned hot and fast, producing copious amounts of ultraviolet light and creating the first heavy elements in their cores. When they died in supernova explosions, they scattered those elements into space, enriching the surrounding gas and paving the way for the next generations of stars and eventually planets. Looking back on that first flicker of creation, it's remarkable how much was decided so quickly. The laws of physics, the makeup of matter, the balance between expansion and gravity, all of it was set in motion within moments. From there, the universe simply had to follow those rules, and those rules were generous enough to allow complexity to grow. It wasn't inevitable that they would be. Small changes in the strengths of forces or the masses of particles could have prevented stars, planets, or chemistry entirely. Still, the path from this point to any form of life was long and winding. The young cosmos had taken its first steps toward complexity, but the conditions we associate with living worlds were far over the horizon. Even so, the story was moving in that direction. In the dense knots of matter forming deep in space, the first seeds of starlight were nearly ready to spark, and with them would come the next stage in the universe's slow preparation for life. The story shifts naturally to the time when those first stars appeared and began reshaping the cosmos in ways that would eventually make planets, oceans, and living cells possible. Their birth was both a transformation and a signal that the universe was entering a new era, one in which light and heavy elements would begin to weave the fabric of worlds. The earliest universe was not empty space dotted with stars. It was more like an enormous cauldron, if you can picture such a thing, though in reality there was no container, no walls, and no place to stand outside looking in. Everything that would ever exist was suspended in an all-pervasive medium of particles and radiation, constantly interacting. The temperatures and densities were so extreme that the concept of solid, or liquid, or even gas didn't apply. Everything was a fluid of energy and matter, moving and colliding in ways that only high-energy physics can describe. This is what scientists mean when they refer to the early universe as a cosmic soup. The recipe was simple in terms of ingredients: quarks, gluons, electrons, neutrinos, photons, but the conditions made their interactions incredibly complex. The quarks were not yet locked together inside protons and neutrons. Instead, they roamed freely in a plasma, bound only temporarily before breaking apart again. Gluons, the particles that normally hold quarks together, moved just as freely, constantly binding and unbinding in the seething mix. To understand why it behaved this way, it helps to remember that at extremely high temperatures, the kinetic energy of particles overwhelms the forces trying to hold them together. Imagine trying to stack blocks in a hurricane. The wind's energy simply tears them apart faster than you can connect them. In the same way, the early universe's heat prevented quarks from settling into stable arrangements for more than fleeting moments. But expansion was already at work. The space itself was stretching, and as it did, the energy density dropped. The temperature fell, not evenly, but fast enough that the average conditions began changing in meaningful ways. Within microseconds, the quark-gluon plasma cooled to the point where quarks began combining into protons and neutrons. This was the first step toward a chemistry of any kind, although still far removed from what we'd recognize as chemical reactions. Alongside these developments, neutrinos were moving almost unhindered. These extremely light particles interact only through the weak nuclear force and gravity, so they scarcely noticed the dense plasma around them. Within the first second, they effectively decoupled from the rest of the matter, beginning a journey through space that has continued for billions of years. They form what we now call the cosmic neutrino background, though detecting them is far more difficult than observing the cosmic microwave background. In these same early seconds, photons were still tightly coupled to matter. They bounced repeatedly off electrons, unable to travel in straight lines for any significant distance. This constant scattering meant that the universe was completely opaque to light. Nothing like a sunrise or starlight could exist yet. The glow was everywhere, but no point of light could shine through. The soup was bright in an all-encompassing way, but there was nothing to distinguish one part of it from another, except for the faintest variations in density and temperature. The composition of this soup was overwhelmingly hydrogen in the form of protons, and helium nuclei formed soon after, with trace amounts of lithium and beryllium. These came from Big Bang nucleosynthesis, a short but crucial period that took place between about 10 seconds and 20 minutes after the Big Bang. In that window, the density and temperature were just right for nuclear fusion to occur before expansion thinned things out too much. For life as we know it, these light elements are only part of the picture. Hydrogen is essential for water and organic molecules, and helium is important in stellar physics. But elements like carbon, nitrogen, oxygen, phosphorus, and sulfur, the backbone of biology, were completely absent. This meant the soup was not yet ready to form planets, oceans, or cells. Instead, it was laying the groundwork for the stars that would one day create those heavier elements. Even in the absence of complexity, the balance of ingredients was vital. The exact ratios of hydrogen to helium influence how stars burn and evolve. Too much helium, and the first stars might have formed differently, altering the chemical evolution of the universe. Too little, and their lifespans and fusion processes might have been drastically different. The Big Bang produced a ratio of about 3 hydrogen atoms for every 1 helium atom by mass, a balance that turned out to be remarkably well suited for star formation over billions of years. In the hundreds of thousands of years that followed, the soup cooled enough for electrons to combine with nuclei, forming neutral atoms. This period, called recombination, marked the point when photons could finally travel freely. The light from that moment still exists as the cosmic microwave background, stretched into microwaves by the ongoing expansion of the universe. Its near uniformity tells us that the soup was astonishingly well mixed, with only tiny fluctuations, about 1 part in 100,000 in density. Those small differences were the seeds from which all later cosmic structure would grow. The importance of those fluctuations can't be overstated. Without them, matter would have remained evenly spread out, and gravity would have had nothing to pull into clumps. Stars, galaxies, and planets would never have formed. The soup would simply have expanded and thinned forever, remaining a dim, diffuse haze. But because of those slight irregularities, some regions had just enough extra mass to start collapsing under their own gravity, a process that would eventually light the first stars. In the cosmic soup stage, there were no places that could have supported life, but there were already the physical laws and constants that would allow life to exist later. Gravity worked with the strength it does today. Electromagnetism governed the behavior of charged particles, and the nuclear forces held atomic nuclei together with the same reliability they do now. The universe was chemically simple, but physically complete. When scientists study this period, they often use particle accelerators on Earth to recreate, for the briefest moments, the conditions of the quark-gluon plasma. By smashing heavy ions together at near-light speeds, they can reach temperatures of trillions of degrees, briefly freeing quarks from their proton and neutron prisons. The results match predictions from cosmology remarkably well, confirming that our picture of the early soup is not just theory, but supported by direct experimental evidence. The shift from a chaotic particle plasma to a stable mix of light elements was one of the most important transitions in cosmic history. It meant that, from this point onward, matter could act under the influence of gravity to form structures. This soup would thin and cool, but it would also begin to gather very slowly into the patterns that define the universe today. It's strange to think that all the complexity we see now, the billions of galaxies, the stars and planets, the living worlds, emerge from something so simple in composition. In those first hundreds of millions of years, the soup was all there was, and yet, in its simplicity, it held every potential. The hydrogen in your body, the helium in a child's balloon, and the lithium in a phone battery all came from that same primeval mixture. The atoms haven't changed, only their arrangements have. Over time, as the temperature fell and the density dropped, molecular hydrogen began to form. This was a significant step because molecular hydrogen can cool more effectively than atomic hydrogen, radiating away energy and allowing clouds of gas to collapse more easily under gravity. These cooling clouds would become the birthplaces of the first stars. Even here, long before the first light of starlight, the processes that would shape the future were beginning to take hold. The cosmic soup phase lasted far longer in its simplest form than we might imagine, because the pace of change was slow on human timescales. Hundreds of thousands of years passed with only gradual shifts in temperature, density, and the distribution of matter. But gravity never stopped working, and in some parts of the universe, it was already drawing together clouds of gas large enough to one day ignite. By the time the first stars finally formed, the soup had transformed into a more varied mixture. There were still vast stretches of space filled with diffuse hydrogen and helium, but also denser regions where collapse was underway. Those first stars would change everything. They would not only bring light to the darkness, but also create the heavier elements that planets and life depend on. Their birth marked the end of the cosmic soup as the dominant state of the universe, and the beginning of a more structured cosmos. Even though the early universe couldn't support life, it was setting the terms for all the chemistry that would make life possible. The relative abundance of elements, the stability of atomic structures, the presence of cooling mechanisms like molecular hydrogen, all were essential ingredients in the recipe. Without them, there would be no solid surfaces, no oceans, no atmospheres, and no cells. And so, as the first dense clouds prepared to collapse into stars, the soup stage was drawing to a close. It had done its job, providing a uniform base with just enough irregularity to allow growth. The story was shifting toward one of light, heat, and the slow creation of the materials that could one day form living worlds. From here, the appearance of the first stars would begin a cascade of changes, each building on what the soup had made possible. The first lights would mark the next great transition, and their influence would reach across the cosmos. They would reshape the chemical composition of space, ignite processes that had been dormant, and make the universe far more varied than the smooth soup it had been. That's where our attention turns next, following the moment when the darkness gave way to the glow of the very first stars. The young universe had already gone through its most intense rapid changes. The furious rush of its first moments had forged the simplest atomic nuclei and filled space with a uniform glow. Now, after those initial acts of creation, the pace began to shift. It wasn't calm in any human sense. There were still colossal amounts of energy moving through space, particles colliding, and gravity pulling at every patch of matter, but compared to the chaos of the first seconds and minutes, things were slowing down. Cooling was the dominant trend. The expansion of space was carrying particles farther apart, and with that expansion came a steady drop in temperature. At first, the cooling was swift, because the density and energy levels were so high. But as time passed, the rate slowed, and the universe began settling into a more predictable decline in heat. Every part of space was affected in the same way, because on large scales the young cosmos was remarkably uniform. The same processes were happening everywhere, the same soup of particles and radiation thinning out in the same slow, steady rhythm. This stage has sometimes been compared to the moment after a storm, but it's important not to imagine stillness. The cooling was not a quiet in the sense of nothing happening. It was a quiet in the sense of patterns beginning to form, of energy being redistributed into longer, calmer wavelengths. Photons, still bouncing from particle to particle, were gradually losing energy as the fabric of space stretched beneath them. The violent flashes of the early plasma stage gave way to a persistent, softer glow, though no one was there to see it. For hundreds of thousands of years, the temperature remained high enough to keep atoms from forming. Electrons were still bound to no nucleus, zipping freely through the plasma. Every time a proton managed to capture an electron, a nearby energetic photon would knock it loose again. This constant back and forth meant the universe was opaque, light unable to travel far before colliding with something. In a sense, the cosmos was still lit from within, but not in any way that would create beams or shadows, only a uniform brightness that filled every direction equally. The cooling process had an important consequence. As the average energy dropped, certain interactions became less frequent, and others more likely. In the earliest, hottest stages, high-energy collisions could turn particles into different kinds or annihilate them entirely. But now, with less energy available per particle, the mix of matter and radiation began to stabilize. The composition that had been set during Big Bang nucleosynthesis, 3 parts hydrogen to 1 part helium by mass, was locked in. Those elements would remain the dominant ingredients of ordinary matter for billions of years. The uniformity of this stage is one of its most striking features. No matter where you might have been, you would have seen the same conditions, the same density, the same temperature, with only tiny fluctuations here and there. These fluctuations, so small that they were barely measurable even in the cosmic microwave background billions of years later, were the seeds from which all later structure would grow. Gravity was patient, pulling on those slightly denser spots ever so gently, but it would take vast stretches of time for the effects to become obvious. As the universe cooled further, a significant milestone approached. Around 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin. At this point, the average photon no longer had enough energy to ionize hydrogen atoms. Electrons could finally settle into stable orbits around protons, without being immediately freed again. This process, called recombination, transformed the plasma into a transparent gas. For the first time, light could travel unimpeded across space. That light is still travelling today, stretched by cosmic expansion into microwaves. We call it the cosmic microwave background, and it is one of the most valuable pieces of evidence we have about the early universe. It shows us the precise moment when the fog cleared, revealing a cosmos filled with neutral hydrogen and helium. No stars, no galaxies, just the raw materials in a smooth distribution. The transparency of space after recombination marked a turning point. Photons that had once been trapped could now cross the cosmos freely, carrying information about their last interactions with matter. Space itself became a much quieter place for radiation. The constant scattering was over. For matter, however, the story was just beginning. Without the pressure of the radiation constantly bouncing off electrons, gravity could begin pulling gas together more effectively. The tiny density variations imprinted in the early plasma now became the starting points for the collapse of matter into clumps. Cooling continued, and as the temperature dropped further, molecules began to form. The most important of these in the early cosmos was molecular hydrogen. Though it was rare compared to atomic hydrogen, it was vital because it could radiate away heat from collapsing gas clouds. Without molecular hydrogen, the first stars might have taken far longer to form, or might not have formed at all in the way they did. This cooling mechanism allowed regions of gas to contract more quickly, overcoming the heat generated by compression. But even with these processes in motion, the timeline remained vast. From recombination to the first stars took hundreds of millions of years. During that time, the universe was in what astronomers call the Dark Ages. The name can be misleading. It wasn't completely dark since the cosmic microwave background still filled space with a faint glow, but in terms of visible light from stars there was none yet. Space was filled with neutral gas, and the only significant changes were the slow growth of gravitational structures. The Dark Ages were a period of preparation. Gravity was working on a grand scale, pulling hydrogen and helium into denser regions shaped in part by dark matter halos. These invisible scaffolds were essential. Without dark matter, which doesn't interact with light but exerts gravitational influence, the process of forming the first galaxies would have been much slower. Ordinary matter alone might not have clumped enough to form stars in the time the universe has existed. During this long cooling phase, the expansion of space was also stretching the wavelengths of all photons, steadily lowering their energy. The universe was getting not only cooler but redder as light shifted toward longer wavelengths. This red shifting is a key feature of cosmic history, and it continues today as galaxies move away from each other. It means that the radiation from the early universe is still with us, just in a form our eyes can't see without specialized instruments. Although nothing resembling life could have existed in this period, it was essential to the eventual possibility of life. The cooling allowed stable atoms and molecules to form, the expansion provided the space for structures to develop, and the gentle pull of gravity began gathering material into the seeds of galaxies. The universe was, in a sense, catching its breath. But in that breathing space, the groundwork for complexity was being laid. If you were to somehow watch this phase in accelerated time, you'd see vast, diffuse clouds of gas slowly thickening in certain regions. The scale would be incomprehensible, with each cloud spanning many light years. The motions would appear glacial, but over millions of years the changes would add up. Small clumps would merge into larger ones, and their centres would grow dense enough to heat up under the pressure of their own gravity. These would be the first stellar nurseries, though they were still far in the future at this point. The cooling also had another important effect. It allowed the chemical processes that would later build complexity to start taking shape. While the Dark Ages were chemically simple, the presence of molecular hydrogen was a preview of what could come. In later epochs, as heavier elements appeared, those same processes would produce water, carbon dioxide, methane, and the other molecules central to biology. Without this early cooling phase, the timing and distribution of those later molecules might have been very different. Over time, the smoothness of the early gas began to give way to a more textured universe. The faint imprints of sound waves in the plasma before recombination, known as baryon acoustic oscillations, left patterns in the distribution of matter. These patterns, though subtle, influenced how galaxies would eventually arrange themselves on the larger scales. The cooling phase preserved these patterns, locking them into the structure of the cosmos. The phrase, "quiet after the roar," fits in the sense that the most dramatic, high-energy events of the Big Bang's first seconds were over, but the real building work of the universe was just beginning. Cooling was the necessary counterpart to the earlier heat, and without it, nothing we see today could have taken shape. The expansion that drove the cooling also ensured that the universe didn't collapse back on itself immediately, buying the time needed for gravity to work on its grand designs. As the first 100 million years approached, the cooling reached a point where some regions were ready to ignite star formation. The transition from a uniformly glowing plasma to a transparent cooling gas had set the stage perfectly. When the first stars finally formed, they would begin producing the heavier elements needed for planets, oceans, and life. But before that could happen, the universe had to endure this long, slow period of preparation, a phase that was quiet only in comparison to the explosive start. The first lights were close now in cosmic terms, and their arrival would mark the end of the Dark Ages. They would bring not only illumination but transformation, reshaping the chemistry and physics of space, and from those changes would come the conditions under which life could one day appear. The quiet was ending, but its legacy would be written in every atom, every star, and every world that followed. The cooling had prepared the way, and gravity was ready to take the next step. The roar would come again, not from a single moment of creation, but from countless new fires scattered across the dark. When the universe cooled enough for electrons to finally bind with protons and form neutral hydrogen atoms, the change was subtle in the moment, but monumental in consequence. For the first time since the Big Bang, matter could exist in a form that wasn't constantly torn apart by high-energy radiation. That transition, quiet on the cosmic scale, was the foundation for all the chemistry that would follow. Before this point, the hot plasma of protons, electrons, and photons had kept light trapped in a constant cycle of scattering. Every attempt at forming an atom had been undone almost instantly. But at a temperature of about 3000 Kelvin, the photons no longer had enough energy to break apart those newly formed bonds. Electrons could settle into stable orbits around nuclei, producing the simplest and most abundant atom in the universe: hydrogen. Hydrogen, while simple, is far from insignificant. It's the raw material for stars, the primary component of most of the visible matter in the cosmos, and one of the two ingredients in water. It was, and still is, the most common element in existence. Alongside hydrogen, helium atoms were forming as well, though they had actually been forged earlier during Big Bang nucleosynthesis. Helium atoms simply needed the same cooling conditions to capture their own electrons and become neutral. A small trace of lithium joined them, the third and final element produced in measurable amounts during those first few minutes after the Big Bang. These three elements, hydrogen, helium, and lithium, were the entire periodic table at this point in cosmic history. Everything else, from the carbon in living cells to the iron in planets' cores, was still in the future. The chemistry possible in this young universe was limited, but it was stable, and stability was the first requirement for complexity. The formation of neutral atoms had another crucial effect. It allowed light to travel freely through space for the first time. Photons that had been bouncing endlessly from particle to particle could now move in straight lines, without being constantly absorbed and re-emitted. This decoupling of matter and radiation created the cosmic microwave background, a snapshot of the universe as it was at the moment of transparency. Billions of years later, we can still detect this faint radiation, stretched to microwave wavelengths by the expansion of space, and study it for clues about the conditions of that era. While the emergence of neutral atoms is a neat milestone in the timeline of the universe, It wasn't as though stars and planets began forming immediately afterward. The matter in space was still spread too thin, and though gravity had started to pull slightly denser regions together, the process was painfully slow on human terms. The distribution of matter at this point was astonishingly smooth, with only tiny variations, differences of 1 part in 100,000, in density from place to place. Those slight variations were enough, though. Over time, gravity would amplify them, pulling gas toward the regions with just a little more mass. This was the beginning of a large-scale structure formation, but it would take hundreds of millions of years for the results to become visible as galaxies or clusters of stars. In the meantime, the neutral hydrogen and helium gas simply filled space, cooling slowly as the expansion of the universe continued. The chemistry of this period was basic but significant. Neutral hydrogen could occasionally form molecular hydrogen, H2, in very small quantities. This might seem unremarkable, but molecular hydrogen plays an important role in the cooling of gas clouds. Unlike atomic hydrogen, which is poor at radiating away heat, molecular hydrogen can emit infrared radiation effectively, allowing gas to cool and contract more easily. In the later formation of the first stars, this property would prove essential. With the first atoms in place, the universe had crossed an important threshold. Before, the searing plasma made any lasting structure impossible. Now, with stable atoms, matter could gather without being constantly disrupted by high-energy photons. The smooth backdrop of neutral gas was like a blank canvas, awaiting the first brushstrokes of starlight. It's worth remembering that while we talk about these events as steps in a sequence, they were unfolding over enormous stretches of time. From recombination to the appearance of the first stars took roughly 100 to 200 million years. During much of that time, the hydrogen and helium atoms simply drifted in the expanding space, occasionally clumping together in slightly denser pockets, but mostly existing in vast, diffuse clouds. Those clouds were not entirely idle. Inside them, the faint tug of gravity was drawing particles together bit by bit. The denser the cloud, the stronger its gravitational pull, and the faster it could gather more matter. The process was aided by the presence of dark matter, whose invisible gravitational influence helped shape the scaffolding of the early universe. Ordinary matter, the hydrogen and helium atoms, collected in the same places where dark matter had already formed dense halos. While atoms themselves are tiny and simple, their formation was the first real act of cosmic chemistry. Before this, the universe was governed mainly by particle physics, with interactions determined by the high-energy conditions of the plasma. Now, chemistry in the sense we know it, bonding, molecule formation, interactions between atoms, became possible, even if only in rudimentary ways. In these early neutral clouds, collisions between atoms were rare simply because of the vast emptiness between them. The average density of matter was incredibly low, and so the path toward more complex structures required patience on a scale difficult to imagine. But the rules were in place, and the rules favoured gradual gathering. Even at this early stage, the conditions were already tuned toward a universe that could eventually support life. The strengths of the fundamental forces, the mass of the proton and electron, the balance between matter and radiation, all were within the narrow ranges necessary for stable atoms to exist. If any of these values had been even slightly different, atoms might have been unstable, chemistry might have been impossible, and the path to life could have ended before it began. The emergence of the first atoms also marked the end of one kind of universe and the beginning of another. The plasma stage, dominated by radiation pressure, gave way to a matter-dominated cosmos, where gravity would be the main driver of change. This shift allowed the slow collapse of gas into the first structures, ultimately leading to the formation of stars. In thinking about whether the universe could have supported life at this point, the answer remains no, but with an important caveat. While there were no planets, no heavy elements, and no energy sources like stars, the foundation was now in place. The universe had moved from chaos toward order, from a seething plasma to a calm sea of atoms. This was the necessary groundwork for everything that would come after. The coming era would see these atoms gather into the first stars, and those stars would fundamentally change the chemistry of the universe. They would forge the heavier elements needed for rocky planets, oceans, and organic molecules. But all of that depended on the simple step of creating hydrogen and helium atoms and allowing them to persist in a stable environment. From here, the story moves toward the gradual end of the cosmic dark ages. Neutral atoms filled the expanding space, and in their quiet drift, they were slowly falling toward the future sites of the first stars. The chemistry was simple, but the stage was set for the first real burst of cosmic creativity. Gravity was gathering its materials, and the next change would bring the first light the universe had seen since the fading afterglow of the Big Bang. That first light, born from the collapse of hydrogen and helium into nuclear fusion, would mark the start of a new era in which the cosmos became not just a collection of atoms, but a place where complexity could grow. And with that light would come the first steps toward making a universe capable of life. With the first atoms in place, the universe entered a period that would last far longer than the explosive moments that came before it. This was an era without stars, without galaxies, without any visible light except for the fading afterglow of the Big Bang. Astronomers call it the Cosmic Dark Ages, not because there was no radiation at all, but because there were no luminous objects to light up the universe in the way we recognize today. The space between atoms was vast, and the average temperature of the gas was steadily dropping. The glow of the cosmic microwave background was still present everywhere, but it was shifting into wavelengths that no human eye could see. If you could somehow have been present, you would not have been standing in darkness as we think of it. Your eyes would have been useless long before, but you would have been immersed in a cold, uniform bath of neutral hydrogen and helium. This was a universe in transition. It had moved from being radiation-dominated to matter-dominated, meaning that gravity could now take the lead in shaping its future. The smoothness of the gas was not absolute. Those tiny variations in density left over from the earliest moments were still there, invisible but influential. Over millions of years, these small differences began to grow under the pull of gravity. Regions with slightly more matter than their surroundings pulled in more gas, becoming denser still, while emptier regions gave up their matter to the growing clumps. At this time, there were no planets, no moons, no rocky surfaces of any kind. The matter in the universe was entirely in the form of diffuse gas, moving slowly under the influence of gravity. Dark matter, though invisible and undetectable by light, was already playing a critical role. It formed halos, massive, invisible structures that served as gravitational wells into which the ordinary matter could fall. Without these dark matter halos, the gas would have taken much longer to clump together, and the first stars might not have appeared for billions of years, if at all. The gas itself was almost entirely hydrogen, with about 1/4 helium by mass and only trace amounts of lithium. Chemically, it was simple. No carbon, no oxygen, no nitrogen, none of the elements essential for life as we know it. But simplicity was not a flaw here. It was the raw state from which everything more complex would eventually come. Cooling continued throughout the Dark Ages. As the universe expanded, the wavelengths of all radiation stretched, lowering their energy. The temperature of the cosmic microwave background dropped from a few thousand Kelvin at the time of recombination to just a few tens of Kelvin after hundreds of millions of years. The gas cooled more slowly, but it too was gradually losing heat. Molecular hydrogen began to form in small amounts, and this was a turning point in the physics of gas clouds. Molecular hydrogen is far better than atomic hydrogen at radiating away heat, and this cooling allowed clouds to collapse more efficiently. Without this step, the formation of the first stars would have been much slower. Even so, the process was still gradual. From the formation of neutral atoms to the ignition of the first stars took on the order of 1 to 200 million years. During the Dark Ages, the large-scale structure of the universe was taking shape. The initial fluctuations in density grew into a cosmic web, a network of filaments and nodes formed by dark matter, with ordinary matter following the same pattern. Most of the space between these filaments remained almost empty, while the denser regions became the birthplaces of galaxies. This was also a time when the universe was largely transparent to radiation in most wavelengths. Because there were no stars yet, there were no strong sources of high-energy photons to ionize the gas. The hydrogen atoms remained neutral, and space was clear in a technical sense, even if there was nothing bright to see. It's an interesting question to ask whether life could have emerged during the Dark Ages. Based on what we understand, the answer is no, not in any familiar form. The basic requirements for life, solid surfaces, liquid water, complex chemistry, were absent. Without heavier elements, there could be no planets or even dust grains to act as building blocks. Without stars, there was no long-term energy source to sustain metabolism. The conditions were not hostile in the same way as the first few seconds of the universe had been, but they were barren. Still, in this emptiness, something important was happening. The gravitational collapse of gas within dark matter halos was accelerating. Small structures began to merge into larger ones, and the first dense clouds capable of forming stars were assembling. The timing of this process was critical. If the universe had expanded too quickly, the gas would have been too diffuse to form stars before the cosmic temperature dropped too low to allow nuclear fusion. If it had expanded too slowly, gravity might have pulled everything back together into a collapse before stars could form at all. The balance we see today was just right. As the first star-forming regions grew denser, the temperature inside them began to rise. Gravity compressed the gas, and compression generated heat. The competition between cooling through molecular hydrogen radiation and heating from gravitational compression determined when a cloud would finally collapse into a star. Once the center of such a cloud became hot and dense enough, nuclear fusion would begin, marking the birth of the first stars. These first stars, called population T3 stars, were very different from most stars today. With no heavier elements to help cool the gas during their formation, they tended to be far more massive, sometimes hundreds of times the mass of our Sun. Their great size meant they burned through their fuel quickly, living for only a few million years before exploding as supernovae. But in that short time, they changed the universe forever. The light from these first stars ended the Dark Ages. Their intense ultraviolet radiation ionized the hydrogen gas around them, turning it back into plasma and making the universe opaque again in certain wavelengths. Their supernova explosions scattered the first heavy elements, carbon, oxygen, nitrogen, and others, into space. These elements mixed with the surrounding gas, enriching it and setting the stage for the next generation of stars to form with planets around them. From the perspective of our question, whether the universe was ready for life right after the Big Bang, the Dark Ages represent a necessary delay. Life could not appear without stars to forge heavy elements, and stars could not form without this long period of gravitational growth. The cosmic Dark Ages were a waiting period, not in the sense of inactivity, but in the sense of preparation. If you imagine the timeline of the universe as a single year, with the Big Bang at midnight on January 1st and the present day at the next New Year's Eve, the Dark Ages would take up much of the first week. They were not a blink. They were a substantial chapter in the story, during which the first true structures emerged from near uniformity. Even though nothing like life existed yet, the processes unfolding in the Dark Ages were essential for making it possible later. The growth of the cosmic web, the cooling of gas, the assembly of star-forming clouds, all of these were slow, patient steps toward a universe with galaxies, solar systems, and habitable planets. When the first stars finally formed and lit up the sky, they were not just the first sources of light since recombination. They were the first agents of chemical transformation since the Big Bang. Their radiation altered the state of the intergalactic medium. Their winds and supernova reshaped their surroundings, and their heavy elements seeded the clouds that would form the next generation of stars. The end of the Dark Ages was the beginning of a much more dynamic era. Galaxies began to take shape, heavy elements became more common, and the complexity of the universe increased dramatically. But that leap would not have been possible without the long, slow work of gravity during the preceding hundreds of millions of years. The end of the cosmic Dark Ages was not a single moment, but a gradual transition marked by the first lights flickering into being. In the quiet depths of space, after hundreds of millions of years of cooling and gathering, dense clouds of hydrogen and helium began to collapse under their own gravity. They had been forming for a long time, slowly drawn together by the invisible pull of dark matter halos that shape the large-scale structure of the universe. The collapse of a gas cloud into a star is not a quick process. Even under ideal conditions, the journey from a diffuse cloud to a nuclear-burning core takes millions of years. During that time, the cloud must overcome several obstacles. Gravity must pull the gas inward, but the pressure from the gas itself resists compression. As the cloud contracts, it heats up, and that heat pushes outward, opposing gravity. Cooling mechanisms, primarily through the radiation of energy by molecules like molecular hydrogen, are essential to allow the collapse to continue. Without cooling, the gas would simply reach an equilibrium and stop shrinking before it became dense enough to ignite fusion. In the earliest star-forming clouds, molecular hydrogen was scarce, but even in small amounts, it was enough to radiate away just enough heat for gravity to win. The centers of these clouds became denser and hotter, and eventually, the temperature reached about 10 million Kelvin. At that point, the conditions were right for hydrogen nuclei to begin fusing into helium, releasing energy in the process. Nuclear fusion had begun, and with it, the first true stars were born. These first-generation stars, known as Population 3 stars, were very different from most stars in the universe today. With no heavier elements in their composition, they formed with unusual characteristics. Simulations suggest they were often far more massive than the Sun, tens, hundreds, or even several hundred times its mass. The absence of elements like carbon and oxygen meant the cooling of their birth clouds was less efficient, leading to the formation of larger stellar masses. Massive stars burn their fuel quickly. A star 100 times the mass of the Sun might live only a few million years before exhausting its hydrogen and undergoing a catastrophic end. In those short lifespans, however, these stars had an outsized influence on the universe. They were hot, producing enormous amounts of ultraviolet radiation that streamed out into space, ionizing the surrounding hydrogen and ending the cosmic Dark Ages. The birth of the first stars also marked the beginning of a new phase in chemical evolution. Inside their cores, hydrogen was fused into helium, and in later stages of their lives, helium was fused into heavier elements like carbon and oxygen. When these massive stars reached the end of their lives, they exploded as supernovae, scattering those elements into space. For the first time since the Big Bang, the chemical makeup of the universe changed. The pristine hydrogen and helium of the early cosmos became enriched with the building blocks needed for planets, oceans, and life. The energy from these explosions did more than distribute heavy elements. It also stirred and shaped the gas in the surrounding regions. Shockwaves from supernovae compressed nearby clouds, triggering new rounds of star formation. In this way, the first generation of stars not only created the raw materials for later worlds, but also helped set in motion the cycles of birth and death that would continue for billions of years. The formation of galaxies began around the same time as the birth of the first stars. In the densest regions of the cosmic web, multiple dark matter halos and their associated gas clouds began merging together. The gravitational potential wells of these growing structures could hold onto gas even as supernova explosions tried to push it away. As more stars formed within them, these early galaxies became islands of light in a still mostly dark universe. The earliest galaxies were not grand spirals or vast ellipticals like many we see today. They were small, irregular systems, often just a few thousand light years across, containing a few million stars at most, but they represented a major step forward in the organization of matter. For the first time, stars were not isolated points scattered across space. They were bound together in coherent systems, orbiting within a shared gravitational structure. The light from these early stars and galaxies began to ionize the hydrogen in the intergalactic medium. This process, called cosmic reionization, transformed the state of matter in much of the universe. Neutral hydrogen atoms were stripped of their electrons once again, turning vast regions back into plasma. This made the universe opaque to certain wavelengths of light, but in the visible range, it became brighter than it had been since recombination. Reionization was not uniform. It happened in patches, starting around the earlier star-forming regions and spreading outward. Over hundreds of millions of years, these ionized bubbles grew and merged until most of the hydrogen in the universe was ionized again. The process was driven not only by the first stars but also by early galaxies, and possibly even the first supermassive black holes, whose energetic surroundings contributed additional ionizing radiation. The emergence of the first stars and galaxies was the moment the universe became truly dynamic on a large scale. Structures were no longer only shaped by gravity. Radiation, stellar winds, and supernova explosions began to influence the environment in profound ways. Gas was heated, compressed, and enriched with heavy elements, changing how future generations of stars would form. From the standpoint of our question, was the universe ready for life right after the Big Bang? This era represents a critical turning point. It was still far too early for life to appear, at least in any familiar form. Planets had not yet formed, and the environments around these massive first-generation stars were harsh and short-lived. But for the first time, the raw materials of life were being created. The carbon in the backbone of DNA, the oxygen in water, the nitrogen in amino acids. All of these elements were forged in the hearts of massive stars during this period. The earliest galaxies also began the long process of organizing the universe's matter into environments where life could eventually arise. Within their gravitational boundaries, gas could cool and settle into disks, forming stars in more stable, long-lived systems. Later generations of stars, enriched with heavy elements, would form planets in their surrounding disks. Some of those planets would find themselves in regions with the right conditions for liquid water, and on at least one of them, life would eventually appear. The first lights in the universe were not just markers of the end of darkness. They were the start of everything that would follow. Their short but brilliant lives seeded the cosmos with the diversity of elements that make it possible for a rocky planet to have oceans, for an atmosphere to carry oxygen, and for chemistry to give rise to biology. From here, the universe's path toward habitability would depend on how quickly and how widely those heavy elements could spread. The next stages in cosmic history would see galaxies grow larger and more structured. Stars with longer lifespans begin to dominate, and the conditions for planetary systems become more common. The night sky as we know it today, filled with stars and galaxies in every direction, traces its origin back to this era. The faint light from those first stars has been travelling for more than 13 billion years, and with the right telescopes, we can still catch glimpses of it. Each photon from that time is a messenger from a moment when the universe was making its first real steps toward becoming a place where life could exist. The first lights were only the beginning. Their brilliance was brief, but the changes they brought to the cosmos were permanent. With their birth came a transformation in the very nature of the universe, chemically, structurally, and energetically, and in the spaces between those lights, in the gas they enriched and the galaxies they helped shape, the seeds for future worlds were already waiting to grow. The earlier stars, massive and short-lived, were far more than points of light in the young universe. They were the first foundries, the places where the cosmic recipe began to expand beyond the simplicity of hydrogen and helium. In their blazing cores, the universe began making the materials that would someday form planets, oceans, and living things. These stars, often hundreds of times the mass of the Sun, lived fast and died spectacularly. But in between, they reshaped the chemistry of the cosmos forever. Inside the core of a massive star, gravity is constantly pulling inward, compressing the gas to incredible densities and temperatures. That inward force is balanced by the outward pressure from nuclear fusion, the process that powers the star. In its simplest form, fusion takes 4 hydrogen nuclei, protons, and combines them into one helium nucleus, releasing energy in the process. This energy is what makes the star shine, and it is also what keeps it from collapsing under its own weight. In the first stars, this hydrogen to helium fusion was the dominant process for most of their short lifetimes. But as they burned through their hydrogen fuel, the balance began to shift. When hydrogen in the core was depleted, gravity gained the upper hand, compressing the core further and raising its temperature. At these higher temperatures, new fusion reactions became possible. Helium nuclei began fusing into carbon, oxygen, and neon. These reactions released energy too, supporting the star against collapse for a while longer. The process continued in stages, with the core temperature rising each time a lighter element was used up. Carbon fused into heavier elements like magnesium and sodium. Oxygen fused into silicon and sulfur. Each stage happened more quickly than the last, with the final stages lasting only years, months, or even days, compared to the millions of years spent on hydrogen burning. Eventually, in the most massive stars, fusion produced iron in the core. Iron is different from lighter elements in a crucial way. It cannot release energy through fusion. Instead, fusing iron consumes energy, which robs the star of the outward pressure it needs to resist gravity. When the core becomes mostly iron, there is nothing left to stop collapse. The collapse happens in a fraction of a second. Gravity crushes the core to densities greater than those of atomic nuclei. The outer layers fall inward and then rebound violently, creating a shock wave that blasts the star apart in a supernova explosion. This is one of the most energetic events in the universe, briefly outshining an entire galaxy. It is in these explosions, and in the intense conditions just before them, that many of the heaviest elements are formed. The rapid capture of neutrons in the chaos of a supernova creates gold, uranium, and other heavy metals. These elements, along with the carbon, oxygen, and nitrogen made during the star's life, are flung into space at enormous speeds, mixing with the surrounding gas. The term stardust is not just poetic, it is literally true. The atoms in your body, heavier than hydrogen and helium, were forged in stars like these and scattered across space by their deaths. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were once part of a star's nuclear furnace. The universe began with a very short list of elements, and it was in these stellar factories that the list began to grow. The enrichment of the cosmos was uneven at first. The first stars formed in scattered pockets of the universe, and their supernovae enriched only the gas in their immediate surroundings. Over time, as more stars formed and died, the enriched regions expanded. Gas clouds containing heavy elements could cool more efficiently, leading to the formation of smaller, longer-lived stars, population 2 stars, that were different from their massive predecessors. The presence of heavier elements also changed the behavior of star-forming clouds in other ways. Dust grains could form, tiny solid particles made of silicates, carbon compounds, and metals. These grains were important for shielding molecular clouds from radiation, helping them stay cool enough to collapse into stars and planets. They also provided surfaces on which complex molecules could form, including the first organic compounds. The early universe's heavy element production was a kind of feedback loop. The first stars enriched the gas, making it easier for new generations of stars to form in more diverse environments. Those new stars, in turn, produced more heavy elements, further changing the chemistry of space. Over hundreds of millions of years, this cycle gradually transformed the universe from a place with almost no chemical variety into one with the full periodic table available for building planets and life. Galaxies were the places where this process happened most intensely. The gravitational wells of galaxies could hold onto the heavy elements produced by their stars, preventing them from being lost to intergalactic space. In smaller systems, supernova explosions could blow much of the enriched gas away, delaying the buildup of elements. In larger galaxies, the heavy elements could accumulate, leading to rich, complex chemistry earlier in their histories. The factories of heavy elements were not limited to supernovae. In later cosmic history, neutron star collisions would also play a role. When two neutron stars, the dense remnants of massive stars, spiral into each other and merge, they release enormous amounts of energy and eject material rich in heavy elements. Observations of such events in the modern universe confirm that they produce significant amounts of gold, platinum and other R-process elements. While these events were rarer than supernovae, their contributions added another layer of complexity to cosmic chemistry. By the time a few 100 million years had passed since the Big Bang, enough heavy elements had been created and dispersed to allow the formation of the first rocky planets. These planets, orbiting around second and third generation stars, had the potential for stable surfaces, atmospheres, and liquid water, key ingredients for life as we know it. From the perspective of life's timeline, the forging of heavy elements was the single most important development after the formation of the first stars. Without carbon, there could be no organic molecules. Without oxygen, no water or breathable atmospheres. Without nitrogen, no proteins or DNA. Without phosphorus, no cell membranes or energy-carrying molecules like ATP. Every one of these elements was born in the heart of a star and released in its death. The concept that we are made of star stuff, as Carl Sagan famously put it, is more than a poetic statement. It is a straightforward description of the chemistry involved. The atoms in every living thing trace their origins back to the nuclear reactions inside ancient stars. The factories of heavy elements were the first step in turning a chemically simple universe into one capable of complexity. As galaxies grew and merged, the enrichment process accelerated. Larger galaxies could sustain continuous star formation for billions of years, steadily increasing the metallicity, the abundance of elements heavier than helium, in their stars and planets. This gradual increase in metallicity is why older stars in the Milky Way tend to have fewer heavy elements than younger ones. The heavy element factories also had indirect effects on the development of habitable environments. Metals in interstellar gas allow it to cool more efficiently, leading to the formation of smaller, longer-lived stars. These stars, particularly those similar to the Sun, provide stable energy output over billions of years, giving planets in their habitable zones the time needed for life to evolve. By the time the universe was a few billion years old, it had moved far from the chemically pristine state it started with. The heavy element content of galaxies had risen enough that planetary systems were common, and the possibility of life-supporting worlds was widespread. The first lights had set this process in motion, and the factories of heavy elements had given it the materials it needed. The stars that forged the universe's first heavy elements did not end their lives quietly. For the most massive among them, the final act was as dramatic as their beginnings. Explosions so powerful they briefly outshone entire galaxies. These were supernovae, events that not only marked the deaths of stars but also became engines of renewal, scattering the material of those stars back into space, enriching it with the elements needed to build planets, oceans, and eventually life. A massive star spends most of its life in balance. Gravity pulls inward, trying to collapse it, while the energy released from nuclear fusion pushes outward, holding it up. As long as fusion continues, this balance is stable, but the core's fuel is finite, and as each type of nuclear fuel is exhausted, the star moves to the next, fusing heavier and heavier elements in a series of steps. This sequence is rapid in the final stages, Hydrogen burning lasts millions of years, helium burning lasts hundreds of thousands, oxygen burning may last only months, and silicon burning producing iron may last only a few days. Iron, unlike lighter elements, cannot be fused into heavier ones without consuming more energy than it produces. Once a core is made mostly of iron, fusion halts, and with it the outward pressure that resists gravity vanishes. Gravity, no longer balanced, wins instantly. The core collapses in a fraction of a second, and the outer layers fall inward at immense speed. In this moment, several possible fates unfold depending on the star's mass. For many massive stars, the collapsing core is compressed so tightly that protons and electrons merge into neutrons, creating a neutron star. For the most massive stars, the collapse can go further, forming a black hole. In both cases, the infalling material slams into the dense core or the surrounding shockwave, rebounding outward in a titanic explosion. This supernova does more than destroy the star, it reshapes the environment around it. The shockwave plows into the surrounding gas, compressing it, heating it, and sweeping it into expanding shells. The material flung outward carries with it all the heavy elements the star made during its life, plus those created in the extreme conditions of the explosion itself. Gold, silver, uranium, and other process elements are born in these chaotic moments, their atomic structures assembled in microseconds by the rapid capture of neutrons. The energy released in a supernova is almost incomprehensible. In a few days, a single supernova can radiate as much energy as the Sun will emit over its entire 10 billion year lifespan. Much of that energy is carried away by neutrinos, ghostly particles that interact so weakly with matter they pass through entire planets without slowing. But enough energy is deposited into the surrounding gas to have lasting effects. One of those effects is the triggering of new star formation. When the shockwave from a supernova sweeps through a nearby molecular cloud, it compresses the gas, sometimes enough to cause regions to collapse under their own gravity. In this way, the death of one star can set the stage for the birth of many others. The new stars that form from such enriched material inherit the heavy elements of their predecessor, meaning they are born into a universe chemically richer than before. This cycle of stellar birth, death, and enrichment is the foundation of cosmic recycling. The universe began with hydrogen and helium. Stars fused these into heavier elements. Supernovae scattered those elements, and new stars and planets formed from that enriched material. Over billions of years, this process has steadily increased the metallicity of the cosmos, creating more and more environments where rocky planets can form. Not all recycling happens through supernovae. Smaller stars, like those up to about 8 times the mass of the Sun, end their lives less violently, shedding their outer layers into space as planetary nebulae. In these cases, the star's core becomes a white dwarf, and the ejected gas is enriched with carbon, nitrogen, and other elements produced during the star's later stages of fusion. Though less explosive than supernovae, these events still contribute to the chemical enrichment of the galaxy. In the earliest epochs after the Big Bang, the dominant recycling events were the deaths of massive stars. These were the ones that could form quickly from pristine hydrogen and helium, live short lives, and explode as supernovae after only a few million years. Their quick turnover meant that heavy elements appeared in the universe surprisingly soon, perhaps within the first few 100 million years. The chemical fingerprints of this enrichment can still be seen today. Astronomers study ancient stars in the halo of the Milky Way and in small old galaxies to learn about the composition of the gas from which they formed. These stars often have extremely low metallicity, showing they were born before much recycling had occurred. Others, slightly younger, show enhanced abundances of certain elements, indicating they formed from gas enriched by one or a few specific supernovae. The energy and material from supernova also affect the shape and structure of galaxies. Repeated cycles of star formation and explosion can blow bubbles and cavities in the interstellar medium. In some dwarf galaxies, supernova-driven winds can eject much of the galaxy's gas into intergalactic space, effectively shutting down star formation for long periods. In larger galaxies, the gravitational pull is strong enough to hold onto most of the gas, allowing the cycle to continue. From the standpoint of habitability, this recycling process is essential. Without it, planets like Earth could not exist. Rocky worlds require significant amounts of silicon, iron, magnesium, and other metals, materials that simply didn't exist in the early universe. It took generations of stars living, dying, and returning their enriched matter to space to produce enough of these elements for complex planetary systems to become common. This means that the universe could not have been ready for life immediately after the Big Bang, or even after the formation of the first stars. There had to be time for at least one full cycle of massive star formation and supernova death to occur, enriching the interstellar medium with life's building blocks. In reality, it took several cycles, over hundreds of millions to billions of years, to create the abundance of heavy elements we see in systems like our own. Cosmic recycling also ensured that heavy elements did not remain locked away in stellar remnants forever. Neutron stars and black holes keep much of their mass trapped, but the outer layers of exploding stars, and the debris from less massive stars shedding their envelopes, remained free to mix with the galaxy's gas. This mixing was aided by the turbulent motions created by supernova shockwaves and by the rotation of galaxies themselves. The gas enriched by one generation of stars often travelled far from its birthplace before forming new stars. Over time, this meant that heavy elements became more evenly distributed within galaxies, though some regions remained richer than others. Regions near the centres of galaxies, where star formation rates were higher, tended to become chemically enriched faster than the outskirts. In the Milky Way, our Sun formed in a region that had already undergone billions of years of recycling. The cloud that collapsed to form the Sun and the planets contained the debris of countless earlier stars, some massive and short-lived, others smaller and longer-lived. That cloud's composition, with about 2% of its mass in elements heavier than helium, was enough to form a variety of rocky planets, moons, and asteroids. From a cosmic perspective, death and renewal are not separate processes. They are intertwined, each enabling the other. The death of a star is the renewal of the interstellar medium. The renewal of the medium leads to new stars, which will one day die in their turn. This cycle has been running for over 13 billion years, and every atom in our bodies has passed through it in some form. In those disks, dust and gas would coalesce into planets, comets, and asteroids, setting the stage for the environments where life could eventually take root. The universe's readiness for life depended not only on the production of heavy elements, but also on their assembly into stable worlds. In the wake of countless stellar deaths, the raw materials for a new kind of universe were adrift between the stars. Clouds of hydrogen and helium were now laced with heavier elements: carbon, oxygen, nitrogen, silicon, iron, scattered by supernovae and stellar winds. These clouds were not uniform seas of gas anymore. They were becoming rich, textured environments with the capacity to build not just more stars, but the worlds that might circle them. This was the point where the Great Cosmic Kitchen began its work, blending the ingredients that earlier generations of stars had prepared. A molecular cloud, the birthplace of stars and planets alike, is an immense and cold assembly of gas and dust, often hundreds of light years across. The temperatures inside can be just a few tens of degrees above absolute zero, cold enough for atoms to bind together into molecules and for tiny dust grains to survive. The gas is still overwhelmingly hydrogen, but now a small yet crucial fraction is in the form of molecules like carbon monoxide, ammonia, and water vapour. Dust grains made of silicates, carbon compounds, and frozen ices coat the interiors of these clouds, acting both as chemical laboratories and as building blocks for future planets. These clouds are far from static. Turbulence stirs them on every scale, driven by the gravitational pull of nearby masses, the shock waves from earlier supernova, and the rotational motion of the galaxy itself. Within this restless environment, some regions become denser than others. When a dense pocket of gas and dust grows massive enough, its own gravity begins to pull it inward, starting the slow collapse that will ultimately lead to a new star. The collapse of such a region does not gather all of its material into the star. Much of the gas falls inward, but as it does, conservation of angular momentum ensures that not everything can plunge directly into the growing core. Instead, the infalling matter flattens into a disk around the young star, a protoplanetary disk. It is within these disks that the next stage of cosmic mixing and assembly takes place. These disks are not smooth, featureless plains of gas. They are rich in structures, rings of dust, gaps carved by forming planets, spiral arms of denser material, and zones where chemistry is driven by the interplay of heat, radiation, and collisions between particles. The innermost regions are hot, too warm for volatile compounds like water to remain frozen. Farther out, beyond a certain distance known as the frost line, ices can survive and accumulate, providing a reservoir of water and other volatiles for the worlds that form there. Dust grains in these disks collide and stick together, forming larger aggregates over time. At first, the growth is microscopic, with particles joining into clusters only micrometers across. But as collisions continue and electrostatic forces help grains cling to each other, these aggregates grow into pebbles, then into boulders. Eventually, gravitational attraction takes over, allowing kilometre-scale planetesimals to form. These planetesimals are the seeds of planets, capable of pulling in more material and merging with each other in a process that can take millions of years. The composition of a planetesimal depends on where in the disk it forms. Close to the star, rocky materials like silicates and metals dominate, since ices cannot survive the heat. Farther out, ices and other volatile compounds become a significant fraction of the mass. This difference explains why our own solar system has small rocky planets in the inner regions and large gas and ice giants in the outer regions. The same principles apply in other planetary systems forming across the galaxy. The chemical richness of these disks owes its existence to the generations of stars that lived and died before them. The carbon in organic molecules, the silicon in rocks, the iron in planetary cores, all of it originated in stellar interiors. Without that prior enrichment, a protoplanetary disk would be almost entirely hydrogen and helium, making it difficult or impossible to form solid planets at all. The recycling process that filled the cosmic kitchen with these ingredients was essential. The kitchen analogy becomes even more apt when considering the chemical reactions happening within these disks. Dust grains coated with ices act as tiny reaction vessels, where molecules can be assembled under gentle conditions. In the cold outer regions of disks, ultraviolet light from the central star or from nearby stars can drive the formation of complex organic molecules, compounds containing carbon, hydrogen, oxygen, and nitrogen that are relevant to life. Laboratory experiments on Earth have shown that ices containing simple molecules like water, methanol, and ammonia can be transformed by UV light into more complex organics, including amino acid precursors. Comets and asteroids that form in these outer regions act as storage containers for these molecules. In planetary systems, comets can later deliver water and organic materials to rocky worlds in the inner regions, potentially seeding them with some of the chemical building blocks of life. This process, known as late-stage delivery, may have played an important role on early Earth, and it is likely to happen in many other systems as well. The presence of giant planets in a forming system can influence this chemical distribution. Giant planets can act as gravitational shepherds, stirring the disk, redirecting icy planetesimals toward the inner system, and shaping the architecture of the worlds that emerge. In some cases, this can enhance the delivery of volatiles to rocky planets. In others, it can destabilize orbits and cause destructive collisions that hinder habitability. Not all protoplanetary disks are the same. Some are rich in dust and heavy elements, while others are more gas-dominated. The chemical diversity among disks reflects the history of the gas clouds from which they formed. A disk born from gas enriched by several generations of supernovae may have a much higher metallicity, allowing it to form rocky planets more readily. Disks from more pristine gas may produce only gas giants or ice-rich worlds. This stage of cosmic evolution is not just about the creation of stars and planets. It is about the distribution of ingredients in ways that make complex environments possible. The right mix of elements in the right configurations is what allows a rocky planet to have an iron core that generates a magnetic field, a silicate mantle that drives plate tectonics, and an atmosphere capable of supporting liquid water. Without the careful mixing in this cosmic kitchen, those combinations would be rare or non-existent. Even after a planetary system forms, the mixing continues. Impacts between planetesimals, migration of planets through the disk, and interactions with leftover debris all serve to redistribute materials. In our own solar system's early history, Earth is thought to have received much of its water from impacts with icy bodies originating beyond the frost line. Without this delivery, our planet's surface might have remained dry, dramatically reducing the chances for life to arise. The cosmic kitchen is also influenced by timing. A star-forming region rich in massive stars will experience strong stellar winds and radiation that can erode the disks of neighbouring stars, cutting short the time available for planet formation. On the other hand, regions dominated by smaller stars may allow disks to survive for longer, giving planets more time to grow and accumulate complex chemistry. These environmental factors add another layer of variation to the kinds of worlds that can emerge. Over the first billion years after the Big Bang, these kitchens began producing their first batches of complex systems. The earliest planetary systems were likely quite different from ours, often dominated by massive planets close to their stars or by smaller planets with unusual compositions. But as metallicity increased and the diversity of starting materials grew, the range of possible planetary architectures expanded. By the time our Sun formed, about 9 billion years into cosmic history, the kitchen had been stocked with an extraordinary variety of ingredients. The cloud that collapsed to form the solar system contained materials forged in ancient stars, reprocessed in multiple cycles of star formation and death, and blended together in the vast molecular cloud from which our star and planets emerged. In this way, the cosmic kitchen was not just a one-time event, but an ongoing process. Every star system forming today is the result of billions of years of mixing, recycling, and enrichment. Every rocky world, every ocean, every molecule of DNA is a product of this vast, slow, and intricate process that began with the first lights in the universe. The kitchen has prepared the ingredients. Now the assembly begins, turning raw materials into the diverse planetary systems that fill the galaxy. And within some of those systems, the right conditions will come together to make environments where life can emerge. When the dust and gas in a protoplanetary disk begin their slow transformation into planets, the process is both subtle and monumental. From a distance, the disk may seem unchanging, a smooth halo of material around its central star. But within that disk, countless interactions are taking place. Collisions, aggregations, fragmentations, each one a step in the long process of turning scattered grains into fully formed worlds. It is here, in these swirling, flattened arenas of cosmic debris, that the building of planets begins in earnest. The earlier stages are almost invisible on a human scale. Dust grains, each only micrometers in size, collide gently as they are stirred by the turbulent motion of the gas. Static electric charges help them stick together when they touch, forming clusters that grow from tiny specks into grains, then into pebbles millimeters or centimeters across. It seems like a simple step, but it is one of the most important transitions in the planet-forming process. Going from free-floating dust to solid bodies large enough to have their own inertia. Growth from pebbles to larger bodies is a challenge, As objects increase in size, their collisions become more energetic, and impacts can break them apart as easily as they can merge them. In some regions of the disk, rapid growth occurs when pebbles concentrate in certain zones, allowing them to stick together faster than they are destroyed. The presence of gas helps, as aerodynamic drag can slow down the relative motions of pebbles, making gentle collisions more likely. Once objects reach sizes of a few kilometers across, gravity begins to play a larger role. These planetesimals are massive enough to attract more material through gravitational focusing, drawing in nearby pebbles and dust. When two planetesimals collide, they can merge into larger bodies, sometimes tens or hundreds of kilometers in diameter. These growing objects are the seeds of planets, the cores from which larger worlds will emerge. In the inner regions of the disk, where temperatures are high, these seeds are made mostly of rock and metal. In the outer disk, where ices can survive, they also contain frozen water, methane, and ammonia. This difference in composition is one of the main reasons why planetary systems often have small rocky planets close to their stars and giant planets farther out. The icy planetesimals in the outer regions can grow to larger sizes more quickly because they have more solid material available to them. The growth of planetesimals into protoplanets, bodies hundreds or thousands of kilometers in diameter, can take millions of years. During this time, the gravitational influence of these growing worlds begins to shape the structure of the disk. They clear gaps along their orbits, sweep up nearby material, and sometimes eject smaller bodies entirely from the system. In regions where multiple protoplanets form close to each other, gravitational interactions can lead to dramatic collisions, merging two bodies into one or breaking them into fragments that will later reassemble. These giant impacts play a key role in shaping the final characteristics of planets. The Earth's own history likely includes such an event, one in which a Mars-sized body collided with the proto-Earth, ejecting material that eventually coalesced into the Moon. Such impacts can strip away atmospheres, alter a planet's rotation, and even change its chemical composition by mixing materials from deep within different bodies. Farther from the star, where icy planetesimals dominate, a different process occurs. Some of these cores grow large enough, several times the mass of Earth, to begin attracting and holding on to substantial amounts of gas from the surrounding disk. These become gas giants, with thick hydrogen-helium envelopes overlying dense cores of rock, ice, and metal. The timing of this process is critical. If the gas in the disk dissipates before a core reaches the necessary mass, the result is a large icy planet instead of a gas giant. The disk itself does not last forever. Stellar winds, radiation from the central star, and gravitational interactions gradually remove the gas and dust over the course of a few million years. This sets a time limit on planet formation. Any gas giants must form before the gas is gone, while rocky planets can continue to grow through collisions long after the disk has dispersed. The arrangement of planets in a system is shaped not just by where they form, but also by how they move afterward. Planetary migration, driven by gravitational interactions between planets and the gas disk, or between planets themselves, can shift worlds inward or outward from their birthplaces. Some giant planets migrate close to their stars, becoming hot Jupiters. Others move outward or exchange places with neighbouring planets, in a gravitational dance that can last for millions of years. Migration can dramatically affect the chances for habitable planets. A giant planet moving inward might scatter smaller rocky planets out of the habitable zone, or prevent them from forming altogether. But in some cases, migration can help deliver icy bodies into the inner system, bringing water and other volatiles to otherwise dry worlds. Once the major building is complete and the gas has dissipated, planetary systems enter a long period of cleanup. Leftover planetesimals, asteroids and comets remain in large numbers, and their orbits gradually evolve under the influence of the planets. Collisions still occur, sometimes delivering additional water and organics to young planets, sometimes causing massive impacts that reshape or even destroy them. This era of heavy bombardment can last hundreds of millions of years before the system settles into a more stable configuration. The Earth's own early history is a testament to the complexity of this phase. During its first few 100 million years, our planet experienced frequent impacts, some of them large enough to melt substantial portions of its surface. Yet it was also during this time that water arrived in significant quantities, likely from icy bodies originating farther out in the solar system. The balance between destruction and delivery during this phase may have been crucial in setting the stage for life. Every planetary system has its own version of this story, shaped by the mass of the central star, the composition of the disk, the timing of giant planet formation, and the number and size of collisions during assembly. Some systems may end up with tightly packed rocky planets orbiting close to their star, others with widely spaced gas giants and few small worlds. The diversity we see among exoplanets today reflects the countless variations in these initial conditions and evolutionary paths. The readiness of the universe for life depended on this process working in many places. It was not enough to have heavy elements available. They had to be assembled into stable planets in or near the habitable zones of their stars. They had to retain atmospheres, hold on to water, and avoid catastrophic disruptions for long enough for life to take hold. The cosmic kitchen could prepare the ingredients, but only the long, delicate work of planetary assembly could arrange them into environments where biology could emerge. Even in regions where planets formed successfully, the path to habitability was not guaranteed. Some planets ended up too small to hold onto an atmosphere like Mars. Others were too massive and became mini Neptunes with thick, crushing atmospheres. Some worlds were locked in orbits too close to their stars, scorched beyond recognition, while others drifted too far away, freezing into lifeless ice balls. But in the vast number of planetary systems that formed across the galaxy, some inevitably landed in the right conditions. Rocky planets with moderate atmospheres, access to water, and stable climates became the rare but possible oases where chemistry could begin its slow journey toward biology. In these cases, the billions of years of cosmic recycling, mixing, and assembly reached their intended result, a world ready to host life. Once planets have formed, their potential to support life depends on a number of factors, but one of the most critical is their position relative to their star. This is where the idea of the habitable zone comes into play. It is not a magical boundary that guarantees life, but rather a region where conditions are right for liquid water to exist on the surface of a planet. The concept is simple in outline but complex in practice, because it is tied to the physics of heat, radiation, atmosphere, and planetary composition. A star radiates energy, and the amount of energy a planet receives from it depends on two things: the star's brightness and the planet's distance. Too close, and the planet's surface will be too hot for water to remain liquid. It will boil away into vapor. Too far, and any water will freeze solid. The habitable zone is the range of distances where, given a suitable atmosphere, liquid water could persist. For a star like the Sun, this region falls roughly between the orbits of Venus and Mars, though the exact boundaries depend on many variables. The size and location of the habitable zone change depending on the type of star. Smaller, cooler stars have habitable zones much closer in, while larger, hotter stars have zones farther out. But star size also affects the stability of those zones over time. Massive stars burn through their fuel quickly, changing brightness and moving the zone outward in just tens or hundreds of millions of years, too short for complex life to evolve. Smaller stars live for tens or hundreds of billions of years, giving more time for life to develop, but their close inhabitable zones can expose planets to intense stellar activity, including powerful flares and bursts of radiation. Being in the habitable zone is not enough on its own. A planet also needs the right kind of atmosphere to maintain surface temperatures suitable for liquid water. Without an atmosphere, any heat from the star will be quickly lost to space, leaving the planet frozen even if it is technically in the habitable zone. Too thick an atmosphere, and the greenhouse effect can drive temperatures far above the boiling point of water, as happened on Venus. the greenhouse effect itself is a balancing act. Certain gases, like carbon dioxide, methane, and water vapour, trap heat by absorbing infrared radiation and re-emitting it back toward the surface. In moderate amounts, this keeps a planet warm enough for life. In excess, it can create a runaway effect where temperatures rise uncontrollably. In too small amounts, the planet remains cold and inhospitable. A planet's ability to retain an atmosphere depends on its mass, composition, and temperature. Smaller planets have weaker gravity, making it easier for gases to escape into space. If a planet is too close to its star, the increased thermal energy can strip away lighter gases over time. Strong magnetic fields can help protect atmospheres from being eroded by stellar winds, but generating such a field requires an active, molten core, something not all planets have. The composition of the atmosphere also matters for the chemistry of life. On Earth, nitrogen and oxygen dominate, with small amounts of greenhouse gases keeping temperatures in a comfortable range. On a different planet in the same habitable zone, a completely different mix of gases could result in a frozen wasteland or a stifling greenhouse. Even the presence of liquid water itself depends on atmospheric pressure. At low pressures, water can boil away at much lower temperatures than on Earth, making it harder to keep it stable. In our own solar system, the habitable zone is instructive. Venus lies just inside the inner edge. It may have had oceans long ago, but a runaway greenhouse effect boiled them away and left behind a dense, hot carbon dioxide atmosphere, with surface temperatures hot enough to melt lead. Mars lies near the outer edge. It once had flowing rivers and lakes, but its small size allowed much of its atmosphere to escape over billions of years, leaving it cold and dry. Earth sits comfortably in between, with the right mix of distance, atmosphere, and geological activity to maintain stable, life-supporting conditions for billions of years. The stability of a planet's position in the habitable zone is also important. Planetary orbits are not fixed forever. Gravitational interactions with other planets in the system can cause orbits to change over time. A world that spends part of its orbit in the habitable zone and part outside it may experience extreme seasonal or climatic changes that challenge the persistence of life. In some cases, tidal locking can also affect habitability. Planets close to their stars, especially around red dwarfs, can become locked so that one side always faces the star while the other remains in perpetual darkness. This can create temperature extremes, but a thick atmosphere or ocean currents could redistribute heat enough to keep parts of the planet temperate. There are also environments outside the traditional habitable zone where life could exist. Moons orbiting giant planets far from the Sun might have subsurface oceans kept liquid by tidal heating, as in the case of Jupiter's moon Europa or Saturn's moon Enceladus. While these do not fit the classic definition of habitable zone worlds, they expand our view of where life could potentially thrive. However, for the universe's earliest opportunities for life, surface habitability in the zone around a star would have been the most likely starting point. When considering the universe right after the Big Bang, habitable zones as we think of them today did not exist. There were no stars, no planets, and certainly no stable orbits with the right conditions for water. Even after the first stars formed, the planets that might have existed around them would have been in an environment still being bombarded by intense radiation, stellar winds, and frequent catastrophic events like nearby supernovae. It took billions of years for stable habitable zones to exist in significant numbers, filled with planets made from the recycled material of earlier generations of stars. The Goldilocks problem, being not too hot, not too cold, but just right, is really a way of describing a complex set of interdependent factors. Distance from the star is the most obvious, but atmosphere, planetary mass, stellar activity, orbital stability, and even the architecture of the entire system all play roles. A planet can sit in the perfect location and still be uninhabitable if any of these other factors fail. From the perspective of cosmic history, the emergence of widespread habitable zones marks a major shift in the universe's readiness for life. The raw materials had been prepared by earlier generations of stars, and the planets had been assembled in the kitchens of protoplanetary disks. Now, for the first time, there were significant numbers of worlds in the right locations with the right ingredients. Not all of them would go on to develop life, but the potential was there. The arrangement of stars and planets across the cosmos is not random. They are gathered into vast collections bound together by gravity, the great structures we call galaxies. Each galaxy is not only a system of stars and dark matter, but also a complex ecosystem in which the conditions for life are shaped. In the early universe, the galaxies we see today were only beginning to take form, and the environments they created determined much about when and where life could eventually arise. The first galaxies formed only a few 100 million years after the Big Bang, emerging from the densest regions in the web of matter that filled space. At that time, the universe was still recovering from its hot, dense beginnings, and gravity was pulling together clouds of gas and dark matter into compact structures. These earliest galaxies were much smaller than the giant spirals and ellipticals we see today. Many were only a few thousand light-years across, containing far fewer stars than the Milky Way. In these young galaxies, star formation was rapid and intense. The gas within them was still rich in hydrogen and helium, and with little resistance to collapse, vast clouds of it turned into stars at a fast pace. Massive stars dominated these first stellar populations, burning bright and dying young, enriching the surrounding gas with heavy elements. The supernova explosions that followed sent shock waves through the galaxy, triggering more waves of star formation, while also stirring and heating the interstellar medium. These early galaxies were dynamic and often chaotic. The rate of star formation was high, but so was the level of disruption from the very stars being born. In some places, the energy released by clusters of massive stars was strong enough to blow gas completely out of the galaxy, slowing or even halting star formation until more gas could be gathered from the surrounding intergalactic medium. This process meant that early galaxies were in a constant cycle of building and losing, growing, and reshaping themselves. The environments inside these first galaxies were not gentle. The high density of stars meant that supernovae were relatively common, and their radiation and shock waves could be dangerous to nearby planets. If life were to arise in such a place, it would need not only the right planetary conditions but also protection from frequent catastrophic events. However, these same galaxies were also where the first rocky planets would eventually form, since the heavy elements produced by early stars had to accumulate somewhere before being incorporated into new worlds. The location of a star within a galaxy is an important factor for long-term habitability. Near the centre of a galaxy, stars are packed more closely together, and the chances of disruptive encounters with passing stars, intense radiation from supernovae, or bursts from a central black hole are higher. In the outer regions, these hazards are less common, but so is the density of heavy elements, since star formation is slower and fewer supernovae occur to enrich the gas. For a planet to have the best chance of supporting life, it often helps to be in a kind of galactic middle ground, not too close to the crowded active centre, but not so far out that there are too few of the elements needed to build it in the first place. In the earliest galaxies, this middle ground was still developing. Many of these systems were too small to have calm, stable regions for long periods. Their gravitational pull was not always strong enough to keep all of their enriched gas, so much of it was lost to space after bursts of star formation. Over time, though, galaxies merged and grew, creating deeper gravitational wells that could hold onto more gas and build larger, more complex systems. Galaxy mergers played a central role in shaping the environments where life could later appear. When two galaxies collided, their stars generally passed by each other without direct contact, but their gas clouds interacted violently. Compression of the gas during a merger often triggered massive bursts of star formation, rapidly increasing the supply of heavy elements. However, mergers could also be disruptive, scattering stars and altering the orbits of planetary systems, sometimes destabilizing them entirely. In the long run, though, mergers tended to create larger, more stable galaxies with richer chemical diversity. By the time the universe was a few billion years old, some galaxies had grown large enough to sustain steady, long-term star formation without blowing away their gas. In these galaxies, metallicity, the abundance of elements heavier than helium, was high enough to allow rocky planets to form in significant numbers. This was a turning point for habitability on a galactic scale. It meant that there were not only planets with the right ingredients, but also stable environments where they could survive long enough for life to take root. The distribution of heavy elements in a galaxy is never uniform. In spiral galaxies like the Milky Way, the central regions tend to have higher metallicity than the outer edges. This gradient arises because the inner regions have undergone more cycles of star formation and supernova enrichment. For early galaxies, metallicity patterns were less pronounced, but the same principle applied. Regions with more star formation had more heavy elements, and were therefore more likely to produce rocky worlds. Galactic structure also played a role. The first galaxies did not have the well-defined spiral arms we see in modern systems. Many were irregular in shape, distorted by interactions and the uneven distribution of mass. As galaxies matured and settled into more ordered forms, their structures began to influence how stars and planets were distributed. In a spiral galaxy, for instance, the arms are regions of active star formation, while the spaces between them are calmer. This balance between active and quiet zones could provide the varied conditions needed for both the creation of planets and the long-term stability of life-bearing ones. Another important factor in early galaxies was the activity of their central black holes. Even at this early stage, many galaxies harboured massive black holes at their centres, some of which were actively accreting matter. When this happened, the black hole could emit powerful radiation and jets of particles, affecting the gas and stars throughout the galaxy. In the most extreme cases, such activity could sterilize large regions of the galaxy or drive out huge amounts of gas, slowing star formation. However, more moderate activity may have played a role in redistributing gas and influencing the overall evolution of the galaxy. The readiness of the universe for life was tied to the maturity of its galaxies. In small, irregular galaxies, conditions for life were less favourable simply because environments were less stable and resources were more easily lost. In larger, more organised systems, there was room for safe zones to exist, places where planets could orbit in relative calm, far from the chaos of frequent stellar deaths or the disruptive pull of passing stars. As the population of such galaxies increased, so did the number of potentially habitable worlds. Galaxies are not isolated, they exist in groups and clusters, and these larger structures also influence their development. Galaxies in dense clusters may experience more interactions and mergers, which can stimulate bursts of star formation, but also increase the risk of environmental hazards. Those in quieter regions of space may evolve more slowly, but also experience fewer catastrophic disruptions. This variety in galactic environments meant that habitability would never be uniform across the cosmos. It would always be shaped by the history and circumstances of each galaxy. By the middle age of the universe, the balance between star formation, chemical enrichment, and environmental stability had shifted toward conditions more favourable for life. Large spiral galaxies, with rich supplies of heavy elements and a mix of active and quiet regions, became some of the best candidates for hosting life-bearing worlds. In such galaxies, the cradles of possibility were no longer rare. They were scattered throughout the disk, in regions where the balance of resources and stability allowed planets not only to form, but also to keep their delicate conditions for billions of years. From the scale of galaxies, the story naturally narrows again to the scale of time itself. Even in the most promising environments, life does not appear instantly. It requires patience from the cosmos, time for planets to cool, atmospheres to stabilize, and chemistry to experiment with countless combinations before anything living emerges. Understanding why the universe was not ready for life immediately after the Big Bang means understanding why time was not just a backdrop, but a necessary ingredient. Even after galaxies had begun to settle into more structured forms, filled with stars of varying ages and rich in the elements necessary to build planets, the stage was not yet fully set for life. The universe needed more than space and material, it needed time. Time was the silent, invisible factor that allowed all the other processes to play out to completion. Without it, even the most promising environments would have been like half-baked ideas, containing potential but lacking the chance to mature into something sustainable. The earlier stars burned brightly and died young, living for only a few million years. Their intense radiation and violent ends shaped the environment around them, but they did not live long enough to host any sort of biological experiment. Even if planets formed in orbit around them, those planets would have been scorched by ultraviolet light, stripped of atmospheres by stellar winds, and then bathed in the deadly radiation of a supernova. For any chance of life to emerge, more stable stars were needed, stars that could shine steadily for hundreds of millions, if not billions of years. Such stability is tied to a star's mass. Massive stars burn through their nuclear fuel quickly, producing huge amounts of energy, but exhausting themselves in relatively short spans. Smaller stars like the Sun, or even smaller red dwarfs, burn their fuel more slowly and steadily. Red dwarfs in particular can live for tens to hundreds of billions of years, while Sun-like stars enjoy a main sequence lifetime of around 10 billion years. This difference is crucial. A long-lived star gives its planets the time needed to stabilize, to undergo the slow geological and chemical changes that can lead to life, and for that life, if it emerges, to evolve into more complex forms. Time also allows for the accumulation and recycling of heavy elements. After the first generation of massive stars enriched the cosmos with metals, it still took repeated cycles of star birth and death to build up the chemical diversity necessary for complex planets. Carbon, nitrogen, oxygen, and phosphorus, the essential elements for life as we know it, had to be produced and spread widely enough that new planetary systems could incorporate them in significant amounts. That process was not instantaneous. Each cycle of stellar life and death spanned millions to billions of years, and the mixing of materials throughout a galaxy was gradual. Even once a rocky planet forms in a habitable zone, its journey toward being truly habitable is not immediate. A young planet's surface is often dominated by volcanic activity, frequent impacts from leftover debris, and a volatile climate. Early Earth, for example, was bombarded by asteroids and comets during a period known as the Late Heavy Bombardment, roughly 4 billion years ago. This intense activity could sterilize the surface repeatedly, forcing any early life to survive in sheltered environments, like deep underground or near hydrothermal vents. Only after this era calmed down could life have a stable foothold on the surface. Atmospheric evolution is another process that demands patience. The gases a planet starts with are not necessarily the ones that will make it habitable. Outgassing from volcanoes, chemical reactions with the surface, and the delivery of volatiles from comets can all change the makeup of a planet's atmosphere over hundreds of millions of years. On Earth, it took a long sequence of events before the atmosphere reached the balance that could support liquid water and, later, oxygen-dependent life. This included the development of a magnetic field to protect the atmosphere from being stripped by the solar wind, a process tied to the cooling and solidification of the planet's core, which itself took time to stabilize. On a galactic scale, time also allowed dangerous conditions to diminish. In the earliest epochs, the rate of supernovae was higher, meaning radiation hazards were more common. Over billions of years, as star formation rates gradually decreased, so did the frequency of these catastrophic events, especially in the quieter regions of galaxies. This decline improved the chances that planets in those regions could go long stretches without being bathed in harmful radiation from a nearby stellar explosion. Complex life, if it is to arise, is especially demanding of time. On Earth, the earlier signs of life appeared relatively quickly, perhaps within a few 100 million years of the planet cooling enough for liquid water to exist. But those early life forms were simple, single-celled organisms. It took another 2 billion years before multicellular life became common, and nearly 4 billion years before intelligent life appeared. This enormous timescale highlights the fact that even under favourable conditions, evolution does not happen overnight. It requires countless generations of organisms adapting to their environments, accumulating small changes that, over deep time, lead to entirely new forms. The pace of evolution is influenced by planetary stability, continents shift, climates fluctuate, and asteroid impacts occur, all of which can reset or accelerate evolutionary progress. Too much instability can keep life from advancing beyond simple forms. Too little change can slow adaptation, leaving organisms less able to cope with future shifts. Over billions of years, Earth experienced just enough variation to drive adaptation without completely wiping out the biosphere, though there were several mass extinction events along the way. Time also plays a role in the diversification of habitats. Early on, life may be confined to narrow niches, such as deep-sea vents or sheltered ponds. Over millions of years, as climates stabilize and ecosystems develop, life can spread to new environments, becoming more resilient and complex. The diversity of life forms on a planet increases the chances that some will survive environmental changes, making the biosphere as a whole more robust. When we look at the universe's history, it becomes clear that its readiness for life was not a single moment, but a gradual transition. In the first billion years, the essential elements for life were only beginning to be produced. In the next few billion, those elements were incorporated into planets, some of which formed in habitable zones around long-lived stars. But even then, the planets themselves had to go through long periods of geological and atmospheric evolution before becoming truly suitable for life. It is possible that life arose relatively early somewhere in the universe, perhaps only a few billion years after the Big Bang, on a world that happened to have the right combination of ingredients and stability. But the odds of that happening were lower than they are now, simply because the conditions had not yet been optimized by time. The more cycles of stellar enrichment that occurred, the more common rocky planets with the right chemistry became. The more galaxies matured, the more stable and diverse their environments grew. Time widened the window for life, both in the number of suitable locations and in the quality of those environments. Patience in this cosmic sense is not just the absence of change, it is the slow layering of countless changes into something more complete. Every star that lived and died, every cloud of gas that collapsed into a new system, every planet that endured its own violent youth, contributed to the readiness of the universe for life. The universe did not rush this process, and in doing so, it created a far richer tapestry of possibilities than could have existed in its first few billion years. Even now, more than 13 billion years after the Big Bang, the process continues. New stars and planets are still forming, enriched by the remains of countless earlier generations. Some of these worlds will take billions of years to become habitable, while others may already be well along that path. Time ensures that somewhere, life is always either beginning, evolving, or recovering from the last great upheaval. Even with the patience of billions of years, the universe did not become a perfectly safe environment. Time could reduce some threats, but others were inherent to the very processes that built stars, planets, and galaxies. These hazards were part of the same machinery that made life possible, and in the early universe, they were often more frequent and more intense than they are now. For a planet to keep its habitability long enough for life to take hold, it would have to survive not just the trials of its own formation, but the dangers of the cosmic neighborhood in which it found itself. One of the most obvious and dramatic threats came from the deaths of massive stars. Supernova explosions, while essential for scattering heavy elements across space, also released vast amounts of energy in the form of radiation and high-speed particles. A nearby supernova could strip away a planet's atmosphere or flood its surface with harmful ultraviolet and gamma radiation. In the early universe, when massive stars were more common and star formation rates were higher, the frequency of supernovae was far greater. That meant that many regions of galaxies were constantly exposed to the risk of these destructive blasts. Distance was the main form of protection. A supernova might only threaten life within a range of a few dozen light-years, but in crowded stellar environments that distance was not always enough to guarantee safety. In smaller, denser galaxies, stars were packed more closely together, making it more likely that a life-bearing planet would find itself within the danger zone at some point in its history. Over billions of years, galaxies grew larger and less densely packed in their habitable regions, but early on, such hazards were difficult to avoid. Even more extreme than a typical supernova were gamma-ray bursts, the most powerful explosions known. These events, often associated with the collapse of massive, rapidly rotating stars or the merger of compact objects like neutron stars, could release as much energy in seconds as the Sun will emit in its entire lifetime. A gamma-ray burst aimed directly at a planet could cause catastrophic atmospheric loss or trigger chemical reactions that destroy protective ozone layers, exposing the surface to harmful radiation. In the early universe, these bursts may have been more common, as the massive low-metallicity stars thought to produce them were more prevalent. The odds of one hitting any given planet were small, but the potential impact was devastating. Active galactic nuclei posed another hazard. In some galaxies, the central supermassive black hole was actively consuming large amounts of matter, producing intense radiation and powerful jets of particles that could extend far beyond the galaxy's core. If a planetary system was too close to such activity, its atmosphere could be stripped or altered, and its surface could be sterilized. The early universe saw more of this activity, since mergers and abundant gas supplies fed many central black holes. Over time, as galaxies matured and their central regions calmed, active galactic nuclei became less common, making certain areas of galaxies safer for life. Radiation hazards were not limited to extraordinary events. Ordinary stellar activity could also be dangerous, particularly for planets orbiting young stars. Many stars go through periods of high magnetic activity, producing frequent flares and bursts of charged particles. Around small red dwarf stars which have close inhabitable zones, such flares could be strong enough to strip atmospheres or at least make surface life difficult. While red dwarfs are long-lived and common, their early years can be especially turbulent, meaning that any life that forms there would either need strong protection, such as an ocean or subsurface habitat, or would have to appear only after the star's activity level subsided. On a more local scale, planetary systems themselves could present dangers. The early stages of planet formation were chaotic, filled with collisions between large bodies. Even after planets formed, gravitational interactions could destabilize orbits, sending asteroids or comets hurtling toward inhabited worlds. Massive impacts could trigger mass extinctions or, in some cases, wipe a planet clean of life entirely. In our own solar system, Earth endured several such impacts, but life either survived in protected environments or re-emerged after the surface stabilized. The frequency and severity of these impacts decreased over time, as most of the leftover debris was cleared away or locked into stable orbits. Cosmic rays, high-energy particles travelling at nearly the speed of light, were another constant hazard. Produced by supernovae, active galaxies, and other energetic processes, these particles could penetrate deep into planetary atmospheres and even into the ground. While Earth's magnetic field and thick atmosphere shield us from most cosmic rays, planets without such protection would be more vulnerable. In the early universe, with more frequent energetic events, the background level of cosmic rays may have been higher, adding to the challenges for life. The structure of galaxies influenced how exposed planets were to these hazards. In the dense central regions, the probability of nearby supernova, gamma-ray bursts and other energetic events was higher. In the quieter outskirts, the main limitation was the lower abundance of heavy elements, which could make rocky planets less common. Over time, as galaxies enriched their outer regions with metals and their centers became calmer, more locations struck a balance between safety and the availability of ingredients for life. Survival in the face of these hazards often depended on layers of protection. A strong magnetic field could deflect charged particles from stellar winds and cosmic rays. A thick atmosphere could absorb harmful radiation. Oceans could shield life from surface-level dangers, allowing it to persist even during periods of heightened activity in the sky. Subsurface habitats, whether in rock or ice, offered even more protection, and it is possible that in many worlds, life began in such refuges before expanding to the surface once conditions improved. The history of life on Earth reflects this interplay of danger and resilience. Mass extinctions have been linked to asteroid impacts, volcanic eruptions, and possibly nearby supernovae. Each time, life was reduced in diversity but not eliminated, and over time new forms emerged to fill the vacated niches. In some cases, these disruptions may even have accelerated evolutionary change by opening opportunities for new species to dominate. The same could be true elsewhere. Hazards could both destroy and, indirectly, foster the conditions for the next stage of biological development. In the early universe, the high frequency of such hazards may have delayed the emergence of life on many planets, forcing them to endure repeated setbacks. But as time went on, and the rate of catastrophic events decreased, the chances of a planet going long stretches without major disruption improved. This allowed more complex ecosystems to develop and persist, increasing the likelihood of intelligent life eventually appearing. By the time galaxies like the Milky Way reached a more mature stage, the balance between hazards and habitability had shifted. There were still dangers. Supernovae, impacts, and stellar activity never disappeared entirely, but they were less frequent, and planets in the right locations could remain stable for billions of years. These calmer periods were when life had its best chances to flourish. From this point in the cosmic story, it becomes important to consider not just survival, but where survival was most likely. The early universe may have been filled with temporary oases where life could begin, only to be erased by the next catastrophe. The early universe may have been abundant with star formation, chemical enrichment, and the raw materials for planets, but it was not evenly generous with stability. Many places were dazzling in their brightness and activity, yet hostile in their capacity to nurture life for any sustained period. The safe zones were rare, scattered among the noise and often transient, temporary shelters that would not last long enough for biology to build anything complex. But as billions of years passed, some regions of the cosmos transformed into true havens, places where the hazards diminished, the resources remained plentiful, and the clock ran long enough for life to evolve without constant interruption. These first safe neighborhoods were not necessarily the largest or most spectacular parts of a galaxy. In fact, their very safety often came from being overlooked by the most violent processes. They tended to form at a careful distance from the galactic core, where the density of stars was lower and the frequency of catastrophic events like supernovae or gamma-ray bursts dropped significantly. Too close to the core, and the risk from nearby stellar explosions or the activity of a central black hole was too high. Too far out, and the abundance of heavy elements might still be too low to build rocky planets rich in the chemical diversity needed for life. The havens emerged in the in-between zones, regions not too crowded, not too sparse, and chemically well supplied. In spiral galaxies like the Milky Way, these regions often lay between the inner bulge and the outer disk, where the balance of metallicity and stability was most favourable. The distribution of heavy elements was crucial. The earlier stars in these zones had already gone through enough cycles of birth and death to enrich the local gas with carbon, oxygen, nitrogen, phosphorus, and iron. all of which are vital for the kinds of complex chemistry that biology demands. But the pace of star formation had slowed enough to reduce the frequency of massive, short-lived stars that would later explode and destabilize the area. This gradual tapering of activity meant that while new stars were still being born, the violence of their deaths was less likely to overwhelm their surroundings. The gravitational architecture of these safe havens also mattered. In calmer regions of the galaxy, stars were spaced farther apart, lowering the odds of disruptive encounters. A close pass by another star could destabilize the orbits of planets, sending them into the cold depths of interstellar space or crashing them into their suns. In the dense stellar neighborhoods closer to galactic centers or in globular clusters, such encounters were more common, making long-term planetary stability rare. In the safer mid-disk regions, these risks were minimized. Even in these quieter neighborhoods, planetary systems needed to be in the right configuration to remain habitable. The presence of giant planets in the outer reaches of a system could help by gravitationally shielding inner rocky planets from frequent asteroid impacts. While no system could avoid impacts entirely, giant planets like Jupiter in our own solar system acted as partial guardians, deflecting or capturing many potential threats. Without such outer giants, a system might face a higher rate of catastrophic collisions that could repeatedly reset the biological clock. Another feature of these havens was the reduced level of background radiation. In the crowded, active regions of the galaxy, high-energy cosmic rays from numerous sources could be more intense, raising the risk of biological damage on planetary surfaces. In calmer areas, far from concentrated clusters of massive stars or energetic black holes, the radiation environment was less extreme. This meant that planets with atmospheres and magnetic fields strong enough to offer partial protection could sustain surface life without forcing it entirely underground or underwater. Over time, these safe neighborhoods became not just possible, but increasingly common. As the universe aged, the average rate of catastrophic events declined, especially in regions where star formation had slowed but not stopped completely. Chemical enrichment reached a plateau where even the outskirts of galaxies began to accumulate the necessary heavy elements for complex chemistry. The variety of planetary systems expanded, and with it the number of potentially habitable worlds. It's important to recognize that these havens were not static. Galactic dynamics constantly reshaped them. Spiral arms rotated, bringing regions in and out of zones of higher star formation. Stars migrated over time, sometimes moving into or out of safer areas. A planetary system might spend hundreds of millions of years in a relatively calm orbit, only to drift closer to a spiral arm where the risks increased again. Stability, therefore, was often a matter of statistical likelihood rather than a permanent guarantee. The Milky Way offers a model for how such neighborhoods could develop. Our solar system's position, roughly halfway between the center and the outer edge of the galactic disk, lies in a region where metallicity is high enough for rocky planets to be common, but far enough from the dense core to avoid the worst hazards. The Sun's orbit also keeps it between spiral arms much of the time, avoiding the regions of intense star formation where supernovae are more frequent. This combination of location, chemical resources, and relative isolation has been one of the quiet enablers of Earth's long history. In the earlier safe havens, the mix of conditions likely varied widely. Some may have been rich in planets but poor in stability, their safety periodically interrupted by passing stellar associations or the gravitational influence of nearby clusters. Others may have been chemically less rich but extremely calm, offering long-term stability at the cost of fewer planets capable of supporting life. Over billions of years, as galaxies evolved, more regions achieved the optimal combination of resources and safety, and the odds of finding a planet like Earth increased. For life to truly take advantage of these havens, it needed time within them. A planet that spent only a short fraction of its history in a safe zone might never get the chance to develop complex ecosystems. Conversely, those that lingered in these neighborhoods for hundreds of millions or billions of years had the luxury of slow, steady biological growth. This is where the interplay between galactic dynamics and planetary resilience became so critical. The most promising worlds were those that not only formed in favourable conditions, but remained in them long enough for evolution to work at its patient pace. In some cases, the safe havens could have hosted multiple worlds with life at the same time, star-forming regions that produce several stable systems within the same quiet zone might, over eons, see life emerge independently on different planets. While there is no direct evidence for this yet, the sheer number of planetary systems in a typical galactic neighbourhood makes it statistically possible. These areas, then, were not just cradles for a single biosphere, but potential incubators for multiple lines of evolution, each following its own path. As the universe continued to age, the expansion of these calmer regions marked a fundamental shift in its readiness for life. What had once been rare and fleeting became, in some galaxies, a stable feature. The number of safe havens increased, and their stability improved. The long intervals of cosmic violence were now interspersed with stretches of peace, long enough to allow for the slow transformation of chemistry into biology. Long before life could take root on any world, the universe was already busy with the quiet work of chemistry. In the dark reaches between stars, in cold clouds of gas and dust, molecules were forming, some simple, others surprisingly complex. These were not yet alive, but they were the precursors to life, the essential raw materials from which the first living systems could one day be built. They were born in shadows, hidden from the heat and glare of stars, where the low temperatures and dense conditions allowed chemistry to proceed in ways that open space could not permit. These dark molecular clouds were the nurseries not only of stars but also of the chemical complexity that life would later inherit. Shielded from harsh ultraviolet radiation by layers of dust, the interiors of these clouds could maintain temperatures only a few degrees above absolute zero. At such low energies, atoms and molecules moved slowly enough to stick together when they encountered each other, sometimes forming weak bonds on the surfaces of tiny dust grains. In this frigid environment, water ice was common, coating grains along with frozen carbon monoxide, methane, ammonia, and other simple compounds. The dust grains themselves acted like microscopic laboratories. Their surfaces provided a stable platform for atoms and simple molecules to meet and react. When a hydrogen atom landed on a grain coated with oxygen, for instance, it could form water. Carbon atoms could link up into chains, eventually becoming more complex organic molecules. The extreme cold slowed down some reactions, but it also allowed fragile compounds to persist without being destroyed by heat or radiation. Over time, these ices could accumulate more elaborate structures. Observations with radio telescopes and space observatories have revealed that interstellar clouds contain amino acids, sugars, and other organic compounds that are considered essential to life on Earth. Glycine, the simplest amino acid, has been detected in the material surrounding young stars, and more complex molecules such as formamide, a versatile precursor in prebiotic chemistry, have been found in cometary comas and interstellar gas. These discoveries suggest that the building blocks of biology were widespread long before planets formed. The chemistry in these cold regions was not limited to the slow accumulation of ices. Occasionally, nearby stars or shock waves from supernovae would disturb a cloud, sending pulses of energy through it. These bursts could trigger reactions that otherwise would not occur in the cold. Ultraviolet light from young stars could break apart molecules, creating reactive fragments that quickly reassembled into new compounds. Cosmic rays, high-energy particles travelling through space, could penetrate deep into the clouds, sparking further reactions. Though potentially destructive, these energy sources also provided variety, increasing the diversity of molecules present. When parts of a molecular cloud collapsed under gravity to form a new star, the chemical legacy of that cloud was carried forward. In the surrounding protoplanetary disk, the same ices and dust grains from the parent cloud became part of comets, asteroids, and planets. The conditions in the disk varied with distance from the star, creating different chemical environments. Near the star, higher temperatures drove off volatile compounds, leaving behind mostly rocky materials. Farther out, where it was colder, ices could survive, locking away water and organic molecules that would later be delivered to inner planets by impacts. This process of delivery was crucial. Even if a newly formed rocky planet in the habitable zone started out dry, bombardment by comets and asteroids could bring it water and organics from the colder reaches of the system. In Earth's early history, such impacts may have been a major source of the molecules needed to start prebiotic chemistry on the surface. The fact that comets today still contain complex organics, including amino acids, is a reminder that space has been a reservoir of life's ingredients for billions of years. The reach of these prebiotic molecules extended beyond individual planetary systems. In the dense environments of early galaxies, material could be exchanged between systems through the movement of dust and gas. Stellar winds, supernova explosions, and even the gravitational interactions between stars could eject material into interstellar space, where it might eventually be incorporated into new star-forming regions. This cosmic mixing meant that the molecules formed in one place could travel far, seeding other parts of the galaxy with the same basic ingredients. One of the striking aspects of this chemistry is its universality. The same processes that formed organics in the molecular clouds of our galaxy were likely at work in others. The laws of physics and chemistry do not change from one galaxy to another, and wherever cold, dense clouds of gas and dust exist, similar reactions can take place. This suggests that the basic building blocks of life are not unique to Earth or even to our corner of the Milky Way, but are likely common features of the universe. However, having these molecules available is not the same as having life. The step from chemistry to biology is vast, involving the organization of molecules into self-replicating systems capable of evolution. But without the raw materials, that step cannot happen at all. In this sense, the slow, patient chemistry of molecular clouds and icy bodies laid the groundwork for everything that followed. The universe's readiness for life depended not only on forming planets in habitable zones, but also on stocking them with the right molecular inventory before they even began their biological experiments. These prebiotic molecules were also resilient. Even after being locked into comets or asteroids for hundreds of millions of years, they could survive the violent process of impact and still be recognizable. Laboratory experiments simulating the conditions of such impacts have shown that many organics can endure extreme pressures and temperatures, or even reform after being temporarily destroyed. This resilience meant that the delivery of life's ingredients was not a fragile process easily undone by heat or shock. The abundance of organics in space also raises the possibility that life's basic chemistry could have been jump-started multiple times, in multiple places, without each planet having to invent the process from scratch. If the early Earth received a steady supply of complex molecules from space, it could have shortened the path from a lifeless surface to a living biosphere. The same would be true for any other world with similar deliveries. This kind of cosmic distribution makes the emergence of life seem less like a rare fluke and more like a natural progression wherever the right environmental conditions exist. Still, the presence of these molecules did not guarantee that life would appear. Local conditions on each planet determined whether they would persist, accumulate, and interact in ways that led toward biology. Some planets might have received an abundance of organics only to lose them to atmospheric loss, sterilizing impacts, or chemical breakdown under harsh radiation. Others might have preserved them but lacked the water, energy sources, or surface stability needed for the next steps. In the places where all the pieces came together, rocky planets in habitable zones, stable climates, protective atmospheres, and a steady influx of complex molecules, the stage was finally set for the transition from chemistry to biology. It was here, in the quiet interplay of molecules on a planetary surface, that life's story could truly begin. The chemistry of the shadows had done its work, and the next chapter belonged to the chemistry of light, water, and the dynamic environments of young worlds. From the vast pool of possibilities scattered across the galaxy, our planet emerged not just as a habitable world, but as one that remained stable long enough for life to flourish and evolve into its present diversity. This was not inevitable. For every Earth-like planet that found the right balance, countless others must have fallen short, undone by hazards, deprived of key resources, or placed in environments too unstable for biology to gain a lasting foothold. Earth's story is not simply one of favourable conditions, it is a tale of timing, location, and a sequence of fortuitous events that could easily have played out differently. The foundation of Earth's good fortune began with its position in the solar system. Sitting comfortably within the Sun's habitable zone, it receives just the right amount of stellar energy to keep water liquid on its surface most of the time. Too close to the Sun, and water would have boiled away, as on Venus. Too far, and it would have frozen, as on Mars. But this balance was not purely a matter of distance. The Sun itself is unusually stable for a star of its type, providing a relatively consistent output of energy over billions of years. Variations in stellar brightness could have pushed the climate toward extremes, but in Earth's case, the fluctuations have been modest enough to allow long-term habitability. The early solar system was a dangerous place, with frequent collisions between planetesimals, asteroids, and protoplanets. Earth's early years were marked by massive impacts, including the giant collision thought to have formed the Moon. That impact could easily have destroyed Earth's habitability, but instead it helped stabilize the planet's axial tilt through the gravitational influence of the Moon. This stability reduced extreme climate swings, allowing for a more predictable seasonal cycle, something that would prove crucial for the development of complex ecosystems later on. Earth's size was another stroke of luck. Too small, and it would not have had enough gravity to hold onto a thick atmosphere or maintain a molten core capable of generating a protective magnetic field. Too large, and its gravity might have retained a dense, suffocating atmosphere more like that of Venus. At just the right mass, Earth could hold onto its air without trapping so much heat that it entered a runaway greenhouse state. Its composition also mattered. The mixture of elements in Earth's crust and mantle provided the raw materials needed for a wide range of chemical processes, including those essential for life. Water, one of the most critical ingredients, did not simply appear on Earth's surface. Some of it likely came from the planet's original building blocks, but a significant portion may have been delivered later by comets and water-rich asteroids during the heavy bombardment phase. These deliveries also brought organic molecules formed in the cold reaches of the solar system, adding to the prebiotic inventory already present. The combination of water, organics, and a stable climate created a chemical landscape ripe for experimentation. The role of Earth's magnetic field in preserving habitability cannot be overstated. Generated by the motion of molten iron in the planet's outer core, the magnetic field deflects charged particles from the solar wind, preventing them from stripping away the atmosphere. Without this shield, Earth might have suffered the fate of Mars, which lost much of its atmosphere over time and became a cold, dry desert. The magnetic field also helps protect surface life from harmful cosmic radiation, particularly in regions where the atmosphere alone is insufficient as a shield. Plate tectonics added another layer of stability by regulating the carbon cycle. The movement of Earth's crust recycles carbon dioxide between the atmosphere and the planet's interior, helping to maintain temperatures within a range suitable for life. Without plate tectonics, carbon dioxide could build up to dangerous levels, triggering runaway greenhouse conditions or drop too low, leading to global glaciation. This geological process works on timescales of millions of years, offering a slow but steady thermostat for the climate. The arrangement of the solar system's other planets also played a role. The presence of massive Jupiter in a relatively distant orbit helped shield Earth from some comet and asteroid impacts, though it also occasionally redirected them inward. The overall architecture of the solar system, with gas giants in the outer regions and rocky planets closer in, allowed Earth to exist in a relatively protected zone where destructive collisions became less common over time. The stability of Earth's orbit over billions of years has been another key factor. While gravitational interactions with other planets can cause small variations, Earth's orbit has remained nearly circular, keeping the distance from the Sun, and thus the amount of solar energy received, within a relatively narrow range. Significant orbital eccentricity could have produced extreme seasonal variations, potentially destabilizing climate systems and disrupting the development of life. Even Earth's galactic environment contributed to its luck. The solar system's position in the Milky Way places it far from the crowded, hazardous central regions, yet close enough to the galactic disk to benefit from a rich supply of heavy elements. Its orbit around the galaxy also keeps it between spiral arms much of the time, avoiding the regions where supernova rates are higher. This relatively calm neighbourhood has reduced the number of catastrophic cosmic events Earth has experienced. Once life began, Earth's environment continued to offer the conditions needed for it to persist through multiple global challenges. Ice ages, asteroid impacts, and volcanic eruptions have caused significant disruptions, but none have been severe enough to permanently sterilize the planet. Each mass extinction event was followed by a recovery period, during which surviving species diversified and adapted to fill empty ecological niches. This resilience was possible because the underlying environmental framework, liquid water, breathable atmosphere, and protective magnetic field, remained intact. The fact that Earth's habitability has lasted for billions of years is remarkable when considered against the backdrop of planetary diversity. Many planets likely start with promising conditions but lose them within a few 100 million years due to runaway greenhouse effects, atmospheric loss, or catastrophic impacts. Others may remain habitable in principle, but lack the right mix of chemical ingredients to spark life. Earth's combination of stable energy supply, chemical richness, protective shields, and geological regulation has been rare enough that, even in a galaxy filled with planets, only a fraction may share its long-term stability. Luck, of course, is a relative term. From one perspective, the sequence of events that led to Earth's enduring habitability could be seen as improbable, given the number of things that could have gone wrong. From another, the vast number of planets in the galaxy means that some were bound to have similar sequences, even if they are few in number. Either way, Earth's history shows how multiple layers of favourable conditions built over time can create a world where life not only emerges but thrives for billions of years. For while our planet's history is unique in its specifics, it may not be entirely alone in its general pattern. Other worlds, scattered across the galaxy, may have experienced their own versions of good fortune, combining the right location, resources, and stability to become living planets. The question then becomes how we might recognise them, and what signs their biospheres could leave behind for us to detect across the vast distances of space. While Earth's story is one of favourable timing and a patient unfolding of conditions, it raises the question of whether life could have emerged much earlier somewhere else in the universe. If the right combination of factors came together sooner, long before our sun was even born, there is nothing in principle that would have prevented biology from taking hold. The universe did not wait for Earth to form before producing habitable worlds. Stars and planets existed billions of years earlier, and with them came the possibility that life's spark was struck in places we can only imagine. The earliest planets likely formed around the first and second generations of stars. The very first stars, massive, bright, and short-lived, produced the heavy elements needed for rocky planets. When they exploded as supernovae, they enriched their surroundings with carbon, oxygen, nitrogen, silicon, and iron. In regions of intense star formation, this enrichment could happen relatively quickly, on timescales of a few 100 million years. Once those elements were present in sufficient amounts, rocky worlds became possible, and with them, environments where water and organics could accumulate. If a planet formed in a stable orbit around a long-lived star during these early epochs, and if it received deliveries of water and organic molecules similar to what happened on Earth, it could have begun the long process toward life billions of years before our solar system existed. Such a head start could mean that by the time life first appeared on Earth, some alien biospheres were already ancient, possibly hosting complex life or even civilizations. This is a possibility that shifts our perspective on our place in cosmic history. Humanity could be a latecomer, arriving after countless other worlds had already played out their biological stories. The key limitation for early life was not just the availability of planets, but the stability of their environments. The early universe was more dangerous in many respects. Star formation rates were higher, meaning more frequent supernovae and gamma-ray bursts. Active galactic nuclei were more common, producing radiation hazards for planets near galactic centers. These conditions would have reduced the number of long-term safe zones where life could persist. However, the universe is vast, and even if only a small fraction of regions were calm enough, the absolute number of potential havens could still have been enormous. Metallicity, the abundance of elements heavier than helium, was another factor. Low metallicity environments in the early universe might have produced fewer rocky planets or planets with different compositions, possibly lacking the mineral diversity needed for life. Yet, research suggests that even relatively metal-poor systems can form terrestrial planets, especially smaller ones. These planets might not have been exact analogues to Earth, but they could still have offered stable surfaces, atmospheres, and liquid water under the right conditions. Some of the oldest known stars in our galaxy, over 10 billion years old, are surrounded by planets. A few of these planets are rocky and reside in their star's habitable zone. This discovery alone suggests that habitable environments may have existed when the universe was still less than a third of its current age. Whether any of those worlds hosted life depends on whether they avoided catastrophic sterilization events long enough for biology to take root. If life did emerge early elsewhere, its trajectory would depend heavily on environmental stability. Given the increased hazards of the young universe, many biospheres might have been fragile, repeatedly reset by nearby explosions or climate shifts. Others, in more fortunate orbits and galactic neighborhoods, could have enjoyed uninterrupted development for billions of years. On such worlds, evolution might have progressed beyond anything we can currently imagine, producing ecosystems and perhaps intelligences that rose and fell long before Earth even formed. There is also the possibility of panspermia, the transfer of life, or at least its building blocks, between worlds. In the early, more densely packed regions of galaxies, material could have travelled more readily from one planetary system to another. If life began on one planet, fragments of it could have been ejected by asteroid impacts and later landed on another planet, seeding it with microorganisms. In this way, an early biosphere could have spread its influence across multiple systems, perhaps even across large stretches of a galaxy. The chemical foundation for life, as we've seen, was in place early. Organic molecules form readily in interstellar clouds and on icy bodies, and the processes that produce them do not require a long wait. Water, too, is a common molecule in the cosmos, and once rocky planets formed, there were many ways it could be delivered. The real bottleneck for early life was not chemistry, but the availability of environments where those molecules could persist and interact without being destroyed by external forces. Even in the young universe, there were quiet corners, regions far from the most active star-forming areas, or in the outskirts of galaxies where the density of massive stars was low. These areas might have offered billions of years of uninterrupted stability, giving life ample time to arise. The difference is that such worlds would have been rare compared to later epochs, when hazards declined and safe zones expanded. But rarity on a galactic scale does not mean absence. With hundreds of billions of stars per galaxy, and trillions of galaxies in the observable universe, even a tiny fraction of early habitable planets could have amounted to a vast number. If intelligent life appeared early, it could have had an extraordinary head start over us, billions of years to develop technology, explore and adapt to cosmic changes. That raises the question of why we see no obvious signs of such civilizations. One possibility is that they never arose, with life remaining microbial or simple on most early worlds. Another is that civilizations did emerge but did not last, succumbing to environmental collapse, self-destruction, or simply the limits of their technology. A third possibility is that their presence is subtle or beyond our current ability to detect, hidden in the vastness of space or operating in ways we do not yet understand. Looking for early life beyond Earth means looking deep into the past. The farther we look in space, the further back in time we see. Observing galaxies as they were billions of years ago could reveal signs of planets and atmospheres that existed long before Earth formed. Future telescopes capable of detecting biosignatures, chemical indicators of life in the atmospheres of distant planets, may one day allow us to test the idea of ancient biospheres. Even if we never find direct evidence of life that predates Earth, the fact that the building blocks were widespread so early makes it likely that biology was not confined to our planet's timeline. Life may have been an ongoing experiment throughout the universe's history, beginning in isolated places long before our sun lit up. In that sense, Earth is not the first stage of life's performance, but merely one act in a play that has been unfolding for nearly as long as there have been planets to host it. If the universe could produce life early, and if it continues to create new worlds in calm, stable regions, then the era of life is far from over. The conditions for biology may have existed before us, and they may persist long after we're gone, making life not a fleeting cosmic anomaly, but a recurring theme across the ages. If there is one constant in the story of life's place in the cosmos, it is that the universe has never been in a hurry. From the first flickers of light to the slow settling of galaxies into calmer forms, the readiness for life has been a process measured not in moments but in spans so vast they stretch beyond ordinary human comprehension. Every stage, from the earliest forging of heavy elements to the emergence of stable planetary systems, unfolded at its own pace. There was no single instant when the universe crossed an invisible threshold into being ready. Instead, readiness accumulated gradually, like a slow tide that rises without urgency, yet eventually covers the shore. Looking back across cosmic history, it becomes clear that patience was not just incidental, it was essential. Heavy elements had to be made and spread across space. Stars and planets had to form in safe neighborhoods, far from the chaos that could erase hard-won progress. Water and organic molecules had to be synthesized in the cold recesses of interstellar clouds, stored in icy bodies, and delivered to young worlds. Geological processes had to regulate climates over spans of hundreds of millions of years. At every step, the pace was set by the natural rhythms of physics, not by any imperative to produce life quickly. For Earth, the waiting time was long, but not wasted. Our planet's habitability is the sum of countless influences: its distance from the sun, its size and composition, its magnetic shield, its tectonic activity, and its galactic address, all of which converged into a combination that has persisted for billions of years. But there is no reason to think Earth's timing was unique. Other worlds may have reached similar states much earlier, or may only now be entering their own windows of opportunity. The long patience of the universe means that life's chances are not limited to a narrow slice of time. The conditions that make biology possible have existed for billions of years and will likely continue for billions more. The youngest planets forming today around stable stars could still host life long after Earth has passed into history. In the distant future, red dwarf stars will continue burning steadily for tens or even hundreds of billions of years, offering their planets an almost unimaginable span in which life might arise and evolve. This patience also explains why life, once it begins, can be resilient. Catastrophes happen: asteroid impacts, volcanic winters, radiation bursts, but the long arcs of stability between them allow ecosystems to recover. Even if a planet suffers a mass extinction, as Earth has multiple times, the underlying conditions that support life often persist, allowing new forms to emerge and adapt. In this sense, the universe's readiness is not just about the initial spark, but about providing the long-term shelter in which life can withstand adversity and change. From the perspective of a single human lifetime, this scale can feel almost alien. We live for decades. Civilizations rise and fall over centuries. The idea that planetary and cosmic conditions evolve over spans millions or billions of years is something we can understand intellectually but rarely feel. Yet this is the pace at which life stage is prepared, and it is the tempo to which all living worlds must dance. It means that at any given moment somewhere, life is beginning for the first time, while elsewhere it has been thriving for eons, and in still other places it is ending, leaving behind a planet that may one day host it again. The long patience also shapes our search for life beyond Earth. We're not looking for rare, fleeting miracles, but for processes that the universe has had time to repeat in many locations. The chemistry that underpins biology is not unique to our world. It is a natural outcome of the way matter behaves under certain conditions. The same is true for the formation of planets in habitable zones and the slow accumulation of stable environments. When we point our telescopes toward distant stars and galaxies, we are looking into a long-running experiment, one that began before we existed and will continue long after we are gone. It is humbling to think that we occupy just a brief chapter in this ongoing story. Our emergence was possible because of events set in motion billions of years before our sun ignited. Our survival so far has depended on cosmic quiet that will not last forever. But the patience of the universe means that life is not bound to our timeline. If humanity disappears, the conditions that fostered us will still exist elsewhere, ready to be taken up by other forms, in other places, under other skies. Perhaps the most striking thing about the universe's long readiness for life is that it does not discriminate between the past, present and future. From the earliest stable worlds to those yet to form, the same principles apply. The combination of chemical abundance, environmental stability and time will continue to create opportunities. Life does not have to appear everywhere for this to matter. Even if it is rare in any given place, the scale of the cosmos ensures that it has likely been common across its vast expanse and deep history. And so, as we trace the story from the Big Bang to our own time, what emerges is not a narrative with a single destination, but a pattern, a recurring possibility that takes root wherever and whenever the circumstances align. The universe does not rush to make life, yet it seems unwilling to close off the chance entirely. It waits, allowing stars to form, burn and die, allowing planets to coalesce and cool, allowing water to flow and chemistry to unfold. This waiting is not passive but full of quiet activity, the slow layering of conditions that, when they come together, give rise to something entirely new. From here, our thoughts can wander in any direction. We might picture ancient worlds whose civilizations rose in ages before Earth existed, now silent and lost to time. Or we might imagine planets far in the future, orbiting faint red suns, where life has only just begun to stir. In both visions, the common thread is the same, the universe's patient provision of time and opportunity. And within that vast allowance, life can arise again and again, in forms we might recognize or in forms utterly beyond our current imagining. For those of us alive now, our role is small compared to the age and scope of the cosmos, yet not meaningless. We are one of the ways in which the universe knows itself, one of the voices through which its story is told. Our awareness of its patience is itself a product of that patience. Without billions of years of cosmic preparation, there would be no us to ask these questions, to search for company among the stars, or to wonder about the long arc of life's future. And so, the universe continues, indifferent to urgency, rich in time, offering stage after stage on which life might appear. Some will be brief performances cut short by catastrophe. Others will run for billions of years, evolving complexity beyond anything we have yet seen. We happen to be here during one of these acts, able to look back at what has passed and forward to what may come. And as the stars burn on and the galaxies drift in their slow dances, the patient readiness remains as steady as it has always been. Thank you for spending this time together, drifting through the slow story of the cosmos. I hope the quiet journey left you feeling both curious and at ease. If you've enjoyed this moment of calm exploration, you can always return, and if you'd like more of these gentle, unhurried wanderings through science, you know where to find them. For now, let the thoughts settle, let the noise fade and rest in the long patience of the universe. Until next time, take care.